Far beyond the stars lies a region so empty, it defies belief. A vast, silent stretch of space where galaxies seem to vanish. This is the Boots Void, one of the largest and most mysterious structures in the cosmos. Discovered in the 1980s, it spans hundreds of millions of light years, yet contains almost nothing, no clusters, few stars, just darkness. Scientists still don't understand how it formed, or why it's there at all. Could it be a natural cosmic gap, or the trace of something even stranger? Before we begin, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below and settle in for a fascinating journey. The universe, in our common imagination, is often pictured as a dazzling spectacle, a canvas painted with billions upon billions of sparkling stars, swirling galaxies, and colourful clouds of gas and dust. We envision colossal structures like the Milky Way, our home galaxy, packed with suns and planets, seemingly brimming with light and activity. Beyond our galaxy, we picture countless others, some grand spirals, some fuzzy ellipses, all shining with the collective brilliance of their constituent stars. When we look up at a clear night sky, we see a tiny fraction of this cosmic tapestry, a dense scattering of points of light that hints at an infinite richness stretching beyond our sight. From dazzling nebulae where new stars are born to the spectacular collisions of galaxies that spark cosmic fireworks, the universe often appears to be a place overflowing with material and energetic events. This perception is not entirely wrong. The universe is indeed rich with wonders, and the sheer number of stars and galaxies is truly mind-boggling. However, this image, while captivating, tells only one part of a much larger and more complex story about the architecture of everything that exists. It often overlooks a crucial and profound aspect of the cosmos, its overwhelming emptiness. Space, as it turns out, is not uniformly filled with these luminous objects. Far from it. In fact, for every bright galaxy or shimmering star cluster, there are vast stretches of nothing, or at least what appears to be nothing. These are the truly silent regions of the universe, cosmic expanses where the light from even the most powerful galaxies takes an unimaginable amount of time to traverse, and where the density of matter drops to incredibly low levels. Imagine taking all the sand on all the beaches of Earth and then scattering it across a volume of space larger than our entire solar system. Even then, the individual grains of sand would be so incredibly far apart that the space between them would feel utterly vacant. This analogy, though still imperfect, begins to hint at the profound emptiness that characterizes much of the cosmos. These empty spaces are not just small pockets here and there, they are immense sprawling voids, gargantuan bubbles in the fabric of reality that dwarf even the largest galaxies. They are the truly quiet corners of existence, places where the hum of active galaxies is barely a whisper, and where cosmic silence truly reigns. To understand these empty spaces, we must first adjust our mental image of the universe from a dense, starry field to something more akin to a giant sponge. The galaxies and galaxy clusters, those brilliant beacons of light and matter, are like the knots and filaments of the sponge, concentrated in tangled networks. But between these dense networks are the gaping holes, the areas where the sponge has very little material at all. These holes are the cosmic voids. They are not merely empty in the way that the space between planets is empty, which still contains some dust and charged particles, and is bathed in the light of its star. These cosmic voids are empty on a scale that is difficult for the human mind to fully grasp. They are so expansive that if our entire Milky Way galaxy were placed inside one, it would be a tiny speck, lost in a vast and lonely expanse, with its nearest galactic neighbour perhaps billions of light years away, if any existed within the void at all. The silence in these regions is not just the absence of sound, as sound cannot travel through the vacuum of space, but the absence of light, heat, and gravitational influence from significant masses. It is a profound, deep quiet that speaks of isolation and sheer scale. The emptiness of these voids is relative, of course. No region of space is truly, perfectly empty, not even the deepest void. Even in the most desolate corners, there are still a few stray atoms of hydrogen, perhaps some exotic particles, and certainly the pervasive, though incredibly weak cosmic microwave background radiation, the leftover glow from the Big Bang itself. But the density of this ordinary matter is so incredibly low that it makes the best human-made vacuum chambers look positively crowded in comparison. In a typical galaxy cluster, there might be hundreds or even thousands of galaxies, packed relatively close together. In the filaments that connect these clusters, galaxies are strung out like beads on a necklace. But in the heart of a cosmic void, the number of galaxies can drop to almost zero, or at least to a handful of isolated faint galaxies that seem like cosmic castaways, drifting alone in an ocean of nothingness. This extreme scarcity of visible matter is what gives these regions their characteristically silent and dark nature. Light in these regions is a rare commodity. Stars are few and far between, and the collective glow of distant galaxies is so diluted by the sheer volume of empty space that it becomes imperceptible, like trying to light up an entire continent with a single match. The existence of these vast empty spaces is not some anomaly or mistake in the universe's design. Rather, it is an intrinsic and expected outcome of how the universe has developed since its beginning. According to our best scientific models, the early universe, though incredibly hot and dense, was not perfectly smooth. It had tiny, microscopic variations in its density, little bumps and dips in the distribution of matter and energy. Over billions of years, gravity, the universe's sculptor, has acted upon these initial tiny differences. Where matter was slightly more concentrated, gravity began to pull in even more matter, slowly but surely drawing together gas and dust to form the first stars and then the first galaxies. These regions grew denser and denser, forming the filaments and clusters we see today. Conversely, where matter was slightly less concentrated, gravity had less to work with. These regions were gradually stretched and emptied out as the surrounding matter was pulled towards the denser areas. The overall expansion of the universe also played a crucial role, helping to stretch these already less dense regions even further apart, creating and enlarging the voids. It is a grand cosmic dance of attraction and expansion, constantly shaping the universe into the intricate sponge-like structure we observe. The intriguing aspect of these silent regions is not just their emptiness, but what that emptiness implies about the underlying forces that shape the cosmos. Why isn't the universe a uniform soup of galaxies? Why are they clumped together in such vast structures, leaving behind these enormous gaps? The answers lie deep within the principles of gravity, the nature of dark matter, and the mysterious influence of dark energy, all of which contribute to the segregation of matter into dense walls and empty expanses. The silence of these voids is a profound physical silence, a lack of the vibrant activity that defines galactic neighborhoods. There are no frequent starbursts, no active galactic nuclei blazing with energy, no constant gravitational tugs between nearby galaxies. The few galaxies that do reside within these voids are truly isolated, experiencing a much calmer, less interactive existence than their counterparts in crowded clusters. This isolation means that they might evolve differently, perhaps retaining more of their initial gas, or having fewer star formation bursts triggered by collisions. The concept of a truly empty space, a vacuum, has long fascinated thinkers. But the cosmic voids take this concept to an entirely new level. They are not merely laboratories for studying the absolute minimum of matter. They are immense naturally occurring regions that push the boundaries of what we consider empty. They challenge our intuitive understanding of how matter should be distributed in the universe. If you were somehow transported to the very center of one of these voids, far from any significant gravitational source, the night sky would be a profoundly different and perhaps terrifying sight. Instead of the Milky Way arching overhead or the countless faint smudges of distant galaxies, you might see almost nothing. Perhaps a single faint star or a very distant, almost imperceptible smudge of light from a galaxy, hundreds of millions of light years away, barely visible even with powerful instruments. The nearest bright object might be so far away that its light has taken eons to reach you, giving you a glimpse into a cosmic past, rather than a vibrant present. This profound visual emptiness contributes significantly to the feeling of cosmic silence. a quietude so deep it almost seems to hum with its own stark reality. Moreover, the silence of these voids extends beyond just the visible light. It is also a silence of gravitational influence. While gravity acts across infinite distances, its strength diminishes rapidly with distance. In a void, the nearest large concentrations of mass are so far away that their gravitational pull is incredibly weak. This means that the matter within the void, sparse as it is largely unperturbed by external forces, allowing it to expand with the general expansion of the universe, and perhaps even accelerate in its expansion due to the effects of dark energy. The temperature in these voids would also be extraordinarily low, just a few degrees above absolute zero, warmed only by the faint cosmic microwave background radiation and the occasional distant photon. There is no significant source of heat, no dense gas clouds to compress and warm up, nothing to generate the energetic processes that characterize the brighter, more active regions of the cosmos. This extreme cold and darkness further emphasize the silent and desolate nature of these immense cosmic cavities. The profound emptiness of cosmic voids provides cosmologists with unique laboratories to study the universe. Because these regions are so sparsely populated with ordinary matter, they are excellent places to observe the effects of dark energy, which is thought to be a uniform force acting across all of space. In denser regions, the gravitational pull of matter can counteract or mask the effects of dark energy. But in the vast, empty voids, where gravity from ordinary matter is minimal, the influence of dark energy becomes more pronounced, causing these regions to expand even faster than the universe as a whole. Studying the precise size, shape, and evolution of voids can therefore provide crucial clues about the nature of dark energy, one of the biggest mysteries in modern physics. The silent nature of these regions, therefore, is not a sign of cosmic insignificance, but rather a powerful indicator of the fundamental forces that govern the universe at its grandest scales. They are vast, dark, and seemingly empty, yet they hold deep insights into the secrets of the cosmos, hinting at the subtle, unseen forces that shape the distribution of everything we can see and much that we cannot. The intrigue around these silent regions stems from their ability to challenge our preconceptions of a star-filled sky and reveal a universe far more nuanced and mysteriously structured than we ever imagined. The understanding of our universe has always been a journey of expanding horizons, each new observation revealing a deeper, more intricate reality. For centuries, our view was limited to the stars visible to the naked eye, then to those revealed by early telescopes, and eventually to the recognition of our own galaxy, the Milky Way, as just one of countless others. By the mid-20th century, astronomers began to grasp the vastness of the cosmos, picturing a universe teeming with galaxies, spread relatively evenly throughout space. This grand vision, however, was about to be challenged by a surprising discovery that would highlight the universe's clumpy, uneven nature on a truly colossal scale. It was a moment that reshaped our understanding of cosmic architecture, revealing not just more galaxies, but also immense, gaping holes in the cosmic fabric where galaxies were remarkably absent. This historical moment centered around the identification of the Bhuta's void, a truly giant hole in the universe, an unprecedented discovery that hinted at a much more complex and structured cosmos than previously imagined. The seminal work leading to the discovery of the Bhuta's void was performed by a team of astronomers led by Robert Kirshner. In the early 1980s, Kirshner, along with his colleagues August Umler Jr., Paul Schechter, and Stephen Schechtman, were engaged in a large-scale astronomical survey. Their primary goal was to map the distribution of galaxies across vast regions of space. This was not a simple task of just pointing a telescope and counting dots of light. To truly understand the universe's structure, astronomers need to know not just where galaxies appear on the sky, but also how far away they are. Knowing their distances allows them to create a three-dimensional map, revealing the true cosmic landscape of clusters, filaments, and, as they would soon discover, voids. The method they employed for measuring these immense distances was crucial: redshift. Redshift is a fundamental concept in astronomy, and it served as the key tool for unlocking the universe's grand structure. Imagine a police car speeding away from you with its siren blaring, As the car moves further away, the pitch of the siren sounds lower. This is because the sound waves are stretched out as the source moves away. A similar phenomenon happens with light. When a distant galaxy moves away from us, the light waves it emits get stretched out. When light waves stretch, they shift towards the red end of the electromagnetic spectrum, hence the term redshift. The faster a galaxy is moving away from us, the more its light is redshifted. Edwin Hubble, in the early 20th century, made the groundbreaking discovery that nearly all galaxies are moving away from us, and the farther away they are, the faster they are receding. This relationship, known as Hubble's law, directly links a galaxy's redshift to its distance. By precisely measuring the redshift of a galaxy's light, astronomers can calculate how far away it is. This is the crucial method that Kirshner and his team used. The survey conducted by Kirshner's team involved systematically observing galaxies in a particular direction of the sky. They used powerful telescopes to collect the faint light from distant galaxies. For each galaxy, they would then split its light into its component colours, creating a spectrum. This spectrum contains specific patterns of dark and bright lines, which are like fingerprints that reveal the elements present in the galaxy, and, more importantly for this purpose, how much its light has been redshifted. By carefully analysing these spectral lines and comparing them to patterns from elements on Earth, they could determine the precise redshift of each galaxy. With the redshift in hand, they could then calculate the galaxy's distance from Earth. Repeating this process for thousands of galaxies across a specific region of space allowed them to build a three-dimensional map of galaxy distribution. As they meticulously plotted the positions of galaxies in their survey region, a peculiar pattern began to emerge. In one particularly large section of the sky, extending through the constellation of Bootes, they found remarkably few galaxies. While their instruments were capable of detecting galaxies at those distances, and they were finding galaxies both closer and farther away from this particular region, the middle ground appeared strangely empty. It was as if there was a giant bubble in space, a vast spherical region, where the expected density of galaxies simply wasn't there. This was not just a small gap. This was an enormous expanse, hundreds of millions of light-years across, containing far fewer galaxies than statistical models predicted for a uniform universe. The initial observation suggested a profound deficit of luminous matter, a cosmic emptiness on a scale that had not been seen or fully appreciated before. The initial discovery, often cited as being around 1981, was followed by years of meticulous data collection and verification. Scientific discovery is rarely a single eureka moment. It involves careful checks, further observations, and rigorous analysis to rule out other explanations. Kirshner's team had to ensure that the apparent void was not simply due to observational biases, such as dust-blocking light, or their telescopes not being sensitive enough to detect fainter galaxies in that particular region. They performed follow-up observations, used different telescopes, and conducted statistical analyses to confirm the reality of this large, underdense region. Their diligent work paid off, and by 1987, they formally announced their discovery to the scientific community in a landmark paper. They named this colossal empty space the Bootes Void, because the region of the sky where it was found lies in the direction of the constellation Bootes, the herdsman. The revelation of the Bootes Void was a significant moment in cosmology for several reasons. Firstly, its sheer size was unprecedented. Early estimates put its diameter at roughly 250 million light-years, making it one of the largest known structures in the universe at the time. To put this into perspective, our own Milky Way galaxy is only about 100,000 light-years across. The Bootes Void was large enough to contain thousands of Milky Way-sized galaxies, yet it contained only a handful. This massive scale immediately indicated that the universe's structure was far clumpier and more segregated than previously thought. Secondly, it provided compelling evidence for the cosmic web theory, which posits that galaxies are not randomly scattered, but are arranged in a vast network of filaments and clusters, surrounding immense, nearly empty voids. The Bootes Void was a striking example of one of these large empty bubbles. The scientific community reacted with both surprise and excitement. The existence of such a large void challenged some simpler cosmological models that predicted a more uniform distribution of matter. It spurred further research into how such structures could form in the early universe, prompting deeper investigations into the role of dark matter and dark energy in shaping the cosmos. The discovery also highlighted the power of large-scale redshift surveys. Prior to this, many astronomers focused on individual galaxies or smaller clusters. The Butter's Void demonstrated the necessity of mapping vast volumes of space to truly understand the universe's large-scale architecture. It showed that the universe was not just a collection of objects, but a vast interconnected system with distinct patterns of density and emptiness. Subsequent observations and more advanced redshift surveys have confirmed the existence of the Butter's Void and other similar, though perhaps smaller, voids. Astronomers have even found a few isolated galaxies within the Butter's Void since its initial discovery, confirming that it is not absolutely empty, but rather extremely underdense. These lonely galaxies within the void are like tiny islands in a vast cosmic ocean, offering unique opportunities to study galaxy evolution in isolation, without the frequent gravitational interactions and mergers that characterize galaxies in denser regions. The methods developed and refined during the discovery of the Butter's Void became standard practice for mapping the large-scale structure of the universe, leading to the identification of countless other cosmic structures, both dense and empty. The Butter's Void, therefore, stands as a monument in astronomical history, a testament to scientific ingenuity, and a powerful reminder that the universe holds profound secrets, often revealed in its most unexpectedly empty corners. Its discovery was not just about finding a hole in space, it was about revealing a fundamental aspect of the universe's grand design, a design that is far more complex and intriguing than we initially imagined, characterized by both dazzling concentrations of matter and vast, silent expanses of nearly nothing. The universe is a place of truly mind-boggling scales, where distances are so vast that our everyday units of measurement become completely meaningless. To talk about the size of a galaxy, let alone a structure that contains many galaxies, we need special units. The most common of these is the light year, which is the distance light travels in one Earth year. Light, the fastest thing we know, moves at an incredible speed of about 300,000 kilometers per second. In 1 year, that light covers approximately 9.46 trillion kilometers. This gives us a sense of just how enormous a light year is, and we need this enormous unit to even begin to describe the dimensions of cosmic objects. Even with this unit, the numbers quickly become staggering, and our human brains, accustomed to distances we can walk or drive, struggle to truly picture what these numbers represent. When we talk about something as large as the Butter's Void, we're talking about a scale that defies easy comprehension, a hole in the universe so immense that it pushes the very limits of our imagination. It is a testament to the vastness of space and the incredible architecture that exists within it, often hidden by the seemingly uniform sprinkle of stars we see on a clear night. When astronomers first began to map this immense cosmic emptiness, their measurements pointed to an astounding size. The Butter's Void was initially estimated to be about 250 million light-years across. Think about that number for a moment. 250 million light-years. That is light travelling for 250 million years just to cross from one side of this void to the other. To put this in perspective, our entire planet Earth is only about 4.5 billion years old. The light from one side of the Butter's Void to the other has been travelling for a period of time that is a significant fraction of our planet's entire existence. This single number, 250 million light-years, immediately sets the Butter's Void apart as something truly monumental, a feature in the universe that is not merely large, but gargantuan, even by cosmic standards where large is a common descriptor. This dimension is not just a line across a picture, it represents a sphere of emptiness, a three-dimensional hole in the fabric of space. To truly grasp the immense size of the Butter's Void, it helps to compare it to objects we are more familiar with, even if those objects are themselves incredibly large. Let us start with our own home, the Milky Way galaxy. The Milky Way is a majestic spiral galaxy, containing somewhere between 100 billion and 400 billion stars, along with vast clouds of gas and dust, and a supermassive black hole at its centre. From one edge of its luminous disk to the other, The Milky Way spans about 100,000 light-years. This means that if you could travel at the speed of light, it would take you 100,000 years to go from one side of our galaxy to the other. Now, let us bring this comparison to the Bootes void. If the Bootes void is 250 million light-years across, and the Milky Way is 100,000 light-years across, then to span the diameter of the Bootes void, you would need to line up 2,500 Milky Way galaxies side by side. Imagine that. A chain of 2,500 galaxies, each as grand and star-filled as our own, stretched out end to end just to cover the distance from one boundary of the void to the opposite boundary. This comparison highlights the staggering emptiness of the Bootes void. If you were to take a single Milky Way galaxy, our entire cosmic home, with all its billions of stars, and place it alone in the very centre of the Bootes void, it would be an incomprehensibly tiny speck within that vast expanse. From a hypothetical vantage point at the edge of this isolated Milky Way, looking out into the void, the night sky would be profoundly different from our own. Instead of the familiar band of stars that makes up our galaxy, or the faint glow of nearby galaxies like Andromeda, you would see almost nothing. The nearest galaxy might be hundreds of millions of light-years away, appearing as a barely discernible smudge, if visible at all, even with powerful telescopes. The feeling of isolation would be overwhelming. There would be no swirling dance of gravitational interactions with other large galaxies, no regular supernovae from nearby stellar populations illuminating the void, just an immense, cold, dark silence, broken only by the distant, faint glow of the most energetic objects at the very edges of this cosmic whole. The void truly would live up to its name, offering a visual and physical representation of extreme loneliness in the universe. The vast space between galaxies in the void is not just a little bit more empty. It is so profoundly vacant that our usual concept of galactic neighbourhoods dissolves entirely. This is not just a region with fewer galaxies. It is a region that has been actively emptied out over cosmic time. Moving beyond our single galaxy, let us consider our local cosmic neighbourhood. The Milky Way is part of a small collection of galaxies known as the Local Group. This group includes our Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and about 50 smaller dwarf galaxies, all gravitationally bound together. The Local Group itself is a relatively compact structure, spanning about 10 million light-years from one side to the other. While this is already a huge distance by human standards, it is still dwarfed by the Bootes void. If you were to try and fit local groups across the diameter of the Bootes void, you would be able to line up approximately 25 local groups. This comparison emphasizes that the Bootes void is not just empty on the scale of individual galaxies, but also on the scale of typical galaxy groups. The density of galaxies within the local group is relatively high compared to the average universe, with our major galaxies interacting and influencing each other. In contrast, the Bootes void represents a space where such interactions are almost non-existent, simply because there are so few galaxies close enough to interact. The sheer lack of galactic company within the void is a defining characteristic of its immense scale. To further appreciate its scale, let us compare the Bootes void to even larger structures in the universe: galaxy clusters and superclusters. Galaxy clusters are enormous collections of hundreds or even thousands of galaxies bound together by gravity. These clusters can span several millions of light-years, typically ranging from 3 to 30 million light-years across. For example, the Virgo cluster, a relatively nearby galaxy cluster that our local group is moving towards, spans about 10 million light-years. A single galaxy cluster, as dense and massive as it is, would occupy only a small fraction of the Bootes void's diameter. You could easily place 10 to 100 typical galaxy clusters side by side just across the width of the Bootes void. The contrast in density is stark. While a cluster is a crowded city of galaxies, the void is a vast empty desert. Even more impressive are superclusters. Superclusters are the largest known structures in the universe, consisting of multiple galaxy clusters and groups that are gravitationally linked, forming long filamentary structures. These cosmic superhighways of galaxies can stretch for hundreds of millions of light-years. For instance, the Laniakea supercluster, of which our local group is a part, spans about 500 million light-years. While the Boots void's diameter of 250 million light-years is slightly less than that of some of the very largest superclusters like Laniakea, it is still larger than many other prominent superclusters. This means that the Boots void is not just larger than individual galaxies or galaxy groups, it is larger than many of the grandest collections of galaxies that the universe has organized itself into. This fact underscores the truly exceptional nature of the Boots void. It is not merely an empty space, it is an empty space on the scale of the universe's most enormous structures, demonstrating that the cosmos is not just clumped, but also profoundly segregated into these vast regions of presence and absence. It is one thing to talk about diameter, but the Boots void is a three-dimensional sphere, a truly gargantuan bubble. When we consider volume, the numbers become even more astonishing, further emphasizing the void's emptiness. The volume of a sphere is calculated using its radius cubed. If we take the radius of the Boots void as 125 million light-years and compare it to the volume of our Milky Way galaxy, which can be approximated as a disk with a radius of 50,000 light-years and a thickness of a few thousand light-years, the difference is astronomical. Even if we simplify the Milky Way to a sphere with a radius of 50,000 light-years for a rough comparison, the ratio of the volume of the Boots void to the volume of the Milky Way is truly immense. For every Milky Way galaxy, there is an equivalent volume within the Boots void that is literally billions of times larger. This means that if you were to try and fill the Boots void with Milky Way-sized galaxies, you would need an unimaginable number of them, far more than the 2,500 that fit across its diameter. The void's volume represents an incredible amount of empty three-dimensional space. It is not just a flat empty circle on a map of the sky. It is a deep, vast, spherical emptiness. This volumetric scale is what truly differentiates a void from mere gaps between galaxies. It is a fundamental absence of galactic structures across an entire volume of the universe. The time it would take to traverse such a colossal distance further solidifies our understanding of the Boots void's immense size and profound isolation. If a theoretical spaceship could travel at 1/10 the speed of light, it would still take over 2.5 billion years to cross the void from one side to the other. For context, life on Earth has existed for roughly 3.5 billion years. So, a journey across the Boots void, even at such an incredibly fast, though currently impossible speed, would take longer than the entire history of multicellular life on our planet. Our fastest human-made probes, like the Voyager spacecraft, travel at speeds measured in tens of kilometers per second. At that speed, traversing the Boots void would take an absurdly long time, far longer than the current age of the universe. This thought experiment highlights the physical separation and the sheer scale of the distances involved. Communication across such a void would be equally challenging, with light signals taking hundreds of millions of years to travel. The loneliness of any hypothetical observer within the void would be absolute, their view of the universe limited to incredibly ancient and distant light, providing a cosmic perspective unlike any other. It is important to remember that when astronomers refer to the Boots void as a hole, or empty, they mean it in a relative sense, on a cosmic scale. No region of space is truly an absolute vacuum, completely devoid of everything. Even in the deepest parts of the Boots void, there are still a few scattered atoms of hydrogen gas, the occasional stray photon of light from the cosmic microwave background radiation, and, crucially, a significant amount of dark matter. However, compared to the average density of matter in the universe, the Boots void is incredibly sparse. While the average density of matter in the universe might be equivalent to a few atoms per cubic meter, in the Boots void, that density could drop to a tiny fraction of that, perhaps less than 1 atom per cubic meter. This makes it one of the most underdense regions known to exist. Despite its vastness and emptiness, astronomers have indeed found a handful of galaxies residing within the Boots void, often referred to as lonely galaxies. These galaxies, perhaps only 60 or so known within this enormous volume, are truly isolated. They are separated by tens of millions of light-years from each other, distances that would be considered immense even in more crowded parts of the universe. This stark contrast between the expected number of galaxies and the observed scarcity further reinforces the concept of the Boots void as a region defined by its monumental lack of visible matter, a true cosmic void of staggering dimensions. Its immense size is not just a number on a page, it is a profound indicator of the universe's large-scale structure, a structure that is far more complex, clumpy, and empty than a simple uniform distribution of galaxies would suggest. The sheer scale of the Bootes void forces us to recalibrate our understanding of the cosmos, revealing a universe that is tapestry woven with both luminous threads of galaxies and vast, dark, silent expanses of nothingness. Understanding the location of the Bootes void within the universe requires us to think about cosmic geography. Just like Earth has continents and oceans, mountains and valleys, the universe also has a grand architecture. It is not a random scattering of stars and galaxies, but rather a vast interconnected network often described as the cosmic web. This web consists of enormous thin strands or filaments of galaxies, interweaving and connecting at massive nodes, where galaxies are clustered together in dense groups. Between these filaments and clusters lie immense, relatively empty regions, which are the cosmic voids. The Bootes void is a prime example of one of these gargantuan empty spaces, sitting prominently within this intricate cosmic tapestry. To pinpoint its location, we first need to understand our own cosmic address, and then branch out to locate this particular great emptiness relative to the grand scale of the universe. Our cosmic journey begins at home, on Earth. Earth is one of 8 planets orbiting our Sun, a star that is just one among hundreds of billions in the Milky Way galaxy. The Milky Way is a spiral galaxy, a vast collection of stars, gas and dust, about 100,000 light-years across. Our Sun is located in one of its spiral arms, about 27,000 light-years from the galactic centre. The Milky Way itself is part of a small collection of galaxies called the Local Group. This group includes our galaxy, the Andromeda Galaxy, and about 50 smaller dwarf galaxies. The Local Group is roughly 10 million light-years across. This Local Group, in turn, is moving towards a much larger concentration of galaxies known as the Virgo Cluster, which is about 55 million light-years away. All of these structures, including the Local Group and the Virgo Cluster, are part of an even larger cosmic structure called the Laniakea Supercluster, a vast gravitational basin of galaxies spanning about 500 million light-years. So, our cosmic address is Earth, Solar System, Milky Way, Local Group, Laniakea Supercluster. This gives us a foundational understanding of our own small corner of the universe. From our vantage point on Earth, the Bootes void appears in the direction of the constellation Bootes, the herdsman. When astronomers first identified this void, they were looking at galaxies in this general area of the sky. It is important to remember that constellations are simply patterns formed by stars that appear close together from our perspective on Earth, even though those stars might be at wildly different distances in 3-dimensional space. Similarly, when we say the Bootes void is in the direction of the constellation Bootes, it means that if you were to point a telescope towards that part of the night sky and then measure the distances to the galaxies you see, you would find this enormous gap. This is not just a flat, 2-dimensional empty patch on the sky. It is a 3-dimensional spherical void, stretching away from us into the depths of space. Its centre is estimated to be approximately 700 million light-years away from us. This distance means that the light from the very centre of the void that we observe today began its journey 700 million years ago, a time when complex life was just beginning to diversify on Earth. The Bootes void does not begin right outside our galaxy. It is located at a considerable distance from the Local Group and even the Laniakea Supercluster. The nearest edge of the Bootes void is estimated to be several hundred million light-years away from us, making it a truly distant feature in the cosmic landscape. Its immense size means that it occupies a significant chunk of the observable universe in that particular direction. So, if we were to imagine a large-scale map of the universe, with our location near the centre, the Bootes void would appear as a gigantic, empty bubble located far beyond our immediate galactic neighbourhood and well outside the bounds of our own supercluster. It is a feature of the distant universe, rather than a local phenomenon. The Bootes void is a textbook example of a cosmic void, a major component of the universe's large-scale structure. The cosmic web is often described as resembling a giant sponge or a network of interconnected soap bubbles. The galaxies and galaxy clusters, like the Laniakea supercluster we belong to, are concentrated along the walls and filaments of this web, where matter has gathered over billions of years due to gravity. The spaces between these walls and filaments are the voids, which are vast underdense regions where very little visible matter exists. The Bootis void is one of the largest and most well-defined of these cosmic bubbles. It sits as a colossal empty space, bordered by the dense filaments of galaxies that form the cosmic web around it. Imagine these filaments as cosmic highways of galaxies, and the Bootis void as an enormous empty roundabout or an abandoned district in between these bustling cosmic roads. It is a fundamental part of the universe's architecture, demonstrating that matter is not evenly spread out, but rather organized into this intricate foam-like structure. Around the Bootis void, astronomers have identified several other large-scale structures. While the void itself is remarkably empty, it is surrounded by denser regions of the cosmic web. For instance, some of the most prominent cosmic structures, such as parts of the Hercules supercluster and the Corona Borealis supercluster, are located in the general vicinity, albeit still at significant distances, acting as the walls that define the void. These superclusters represent massive conglomerations of galaxies, stretching across hundreds of millions of light years. The Bootis void effectively acts as a gigantic boundary, a vast empty buffer zone separating these grand concentrations of galactic matter. It is a region where the gravitational pull of these surrounding superclusters has, over cosmic time, pulled away much of the matter that would otherwise have resided within the void, leaving it increasingly empty as the universe expands. This makes the Bootis void not just an isolated empty space, but an integral part of the larger cosmic network, defining the spaces between the universe's largest structures. To use an analogy, consider a map of the Earth with continents and oceans. The continents, where matter is concentrated, represent the galaxy clusters and superclusters. The vast oceans, with very little land, represent the cosmic voids. The Bootis void is like one of the largest oceans on this cosmic map, a colossal body of nothingness separating the land masses of galactic concentrations. Just as ships rarely encounter land in the middle of a vast ocean, galaxies are exceptionally rare within the Bootis void. This geographical perspective helps to illustrate its place in the grand scheme. It is not an arbitrary empty patch. It is a significant feature that defines the large-scale distribution of matter in the universe, an immense region where the cosmic currents of gravity and expansion have cleared out the galactic waters. While there are many other cosmic voids known to astronomers, the Bootis void remains particularly notable for its immense size and its relatively clear definition. Other voids exist, ranging in size from tens of millions to hundreds of millions of light years. However, the Bootis void was one of the first truly massive voids to be identified, and its exceptional scale made it a benchmark for understanding such structures. It is not unique in being a void, but it is unique in its prominence and the initial surprise it generated due to its gargantuan dimensions. Its position within the cosmic web is typical of large voids, surrounded by the denser filaments and clusters that make up the luminous scaffolding of the universe. Studying where the Bootis void sits in relation to these surrounding structures helps astronomers test models of how the universe evolved. The way galaxies are distributed on the edges of the void, and how the void itself has expanded over time, provides clues about the forces that shaped our cosmos, especially the mysterious dark energy that seems to be pushing space apart and thus enlarging these empty regions. The Bootis void's precise location and its relationship to nearby superclusters and filaments are crucial data points for understanding the dynamic processes that have given the universe its current intricate and often surprisingly empty structure. The common image of the universe often presents a bustling, vibrant cosmos, filled with shining stars and countless galaxies, stretching in every direction. We imagine vast nebulae glowing with the light of newly formed suns, and grand spiral galaxies like our own Milky Way, packed with billions of stellar inhabitants. This view, while awe-inspiring, only tells one part of the story. For every region of cosmic density and brilliance, there exist unimaginably vast areas that are profoundly empty, regions where the very fabric of space is stretched thin, and matter, particularly luminous matter like stars and galaxies, is incredibly rare. These are the truly sparse regions of the universe, and the Buddha's void stands as one of the most prominent and illustrative examples of such cosmic emptiness. When scientists describe a region as sparse, or nearly empty, in the context of the universe, they are speaking of an extreme level of underdensity, a state far more vacant than any vacuum we can create in a laboratory on Earth. It is a condition where the fundamental building blocks of the cosmos are so thinly spread that it challenges our everyday understanding of what constitutes nothingness. To truly grasp what sparse means on a cosmic scale, it helps to consider the average density of matter in the entire universe. Scientists estimate that, if you were to average out all the matter and energy across the vastness of space, the universe would contain, on average, only about 1 hydrogen atom per cubic meter. That is an incredibly low density already. To put it into perspective, the air we breathe has trillions upon trillions of atoms per cubic centimetre, not cubic metre. Even the best vacuum chambers on Earth, which we consider extremely empty, still contain millions of atoms per cubic metre. Now, imagine a region of space where the density is significantly lower than even the cosmic average. This is the condition within a void like Bhuti's. In the heart of the Bhuti's void, the average density of ordinary visible matter is thought to be as low as 1/10 of the cosmic average, or even less. This could mean a density of much less than 1 hydrogen atom per cubic metre, perhaps only a few atoms in a volume equivalent to a large building, or even a city block. This is what truly defines a sparse universe, a region where the fundamental particles that make up stars, planets, and even ourselves are spread so thinly that the space between them is truly immense. The most striking aspect of this sparseness is the profound absence of luminous matter. When we speak of a sparse region like the Bhuti's void, we are primarily referring to the scarcity of galaxies and galaxy clusters. Instead of finding hundreds or thousands of galaxies within a certain volume, as one might in a supercluster, the Bhuti's void contains only a handful. These are not merely regions where galaxies are a little bit further apart. They are areas where the gravitational nurseries that typically foster galaxy formation are almost entirely absent. The visual experience from within such a sparse region would be one of profound darkness. The night sky, instead of being peppered with the visible light of countless distant galaxies, would appear largely black, perhaps with only a few extremely faint, lonely galaxies visible as distant, almost imperceptible smudges of light, often separated by hundreds of millions of light years. There would be no swirling nebulae indicating star formation, no bright stellar nurseries, and certainly no grand galactic collisions lighting up the cosmic night. The lack of light sources contributes significantly to the cosmic silence characteristic of these voids. This absence of luminous matter is not an accident. It is a direct consequence of how matter has been distributed and evolved since the very early moments of the universe. In the nascent universe, there were tiny, very subtle variations in density. Regions that were slightly denser began to attract more matter due to the pull of gravity, growing into the structures we see today, the filaments and clusters of galaxies that make up the cosmic web. Conversely, regions that were initially slightly less dense had less gravitational pull. As the universe expanded, these underdense regions were stretched further and further apart, actively emptying out as the surrounding matter was drawn away towards the denser areas. This process, amplified over billions of years, resulted in the formation of these immense cosmic voids. The sparseness of visible matter within them is therefore a direct imprint of the early universe's conditions and the relentless work of gravity and cosmic expansion. It is crucial to remember that while ordinary luminous matter is incredibly sparse in these voids, the regions are not entirely empty of all forms of matter. Invisible dark matter is also present within these voids, though at a lower density than in the cosmic web's denser regions. Dark matter, which does not interact with light and can only be detected through its gravitational effects, plays a crucial role in the formation of cosmic structures. While it gravitates and clumps together, its distribution is also influenced by the same initial density variations that led to the formation of voids. So, even in the empty Bootes void, there is a pervasive, though tenuous, presence of dark matter. More importantly, dark energy, the mysterious force believed to be responsible for the accelerating expansion of the universe, is thought to be uniformly distributed throughout all of space, including the voids. In fact, voids are considered excellent laboratories for studying dark energy because the gravitational pull of ordinary matter is so weak within them that the effects of dark energy, which acts to push space apart, become more dominant and observable. The continued expansion and increasing emptiness of these voids are partly driven by the influence of this pervasive dark energy. Thus, sparse means a dramatic reduction in ordinary matter, but not a complete absence of all cosmic constituents. The gravitational environment within a sparse region like the Bootes void is vastly different from that in a galaxy cluster. In a cluster, galaxies are constantly interacting, pulling on each other, and sometimes even colliding or merging. This gravitational interplay is a major driver of galaxy evolution, influencing star formation, galaxy shape, and the distribution of gas. In contrast, within the Bootes void, the few galaxies that exist are gravitationally isolated. The nearest large concentrations of matter are hundreds of millions of light-years away, meaning their gravitational influence is incredibly weak. This isolation implies that any matter within the void experiences a much gentler gravitational pull, primarily from the distributed dark matter within the void itself and the very weak pull from the distant galaxy filaments. This lack of strong external gravitational forces means that the sparse matter within the void, including any lonely galaxies, can expand more freely with the universe's general expansion, potentially leading to slower, less disturbed evolutionary pathways for its few galactic inhabitants. The gravitational environment is fundamentally calm, unlike the bustling and gravitationally chaotic environments of galaxy clusters. It is important to distinguish the sparseness of cosmic voids from the general emptiness of intergalactic space. Even in the regions between galaxies within a cluster or a filament, space is mostly empty. However, these intergalactic spaces are still relatively close to large gravitational centers and are often filled with a very tenuous but measurable intergalactic medium, sometimes heated by activity in nearby galaxies. Cosmic voids, however, represent emptiness on a much grander scale, a scale of underdensity that defines entire regions of the universe. The intergalactic medium within a void is even more rarefied and colder than in other parts of the universe, simply because there are so few sources of heat and energy, such as active galactic nuclei or massive star-forming regions. The distinction lies in the sheer volume and the profound lack of significant gravitational sources. Voids are not just empty spaces between two galaxies, they are empty spaces between entire superclusters, defined by the absence of the large-scale structures themselves. This scale of emptiness makes voids distinct and crucial for understanding the universe's large-scale organization. The extreme sparseness of the Bootes void and other similar cosmic voids makes them incredibly challenging, yet immensely valuable, targets for astronomical study. Because there is so little light-emitting matter within them, it is difficult to map their boundaries precisely and to study the few objects they contain. Powerful telescopes must stare for exceptionally long periods to gather enough faint light from the rare galaxies within. However, this very sparseness is what makes them scientifically important. Voids represent regions where the effects of gravity from ordinary matter are minimized. This allows cosmologists to isolate and study the effects of dark energy, which is thought to be uniformly present throughout the universe and acts to accelerate its expansion. By measuring how fast voids are expanding and how their matter content is distributed, scientists can gather crucial data to test competing theories about the nature of dark energy and the overall expansion history of the universe. The sparseness of the Bootes void is not just a curiosity, it is a fundamental property that makes it a powerful cosmic laboratory for understanding the most mysterious forces shaping the cosmos. It is a testament to the universe's intricate design, where even the empty spaces hold profound scientific secrets, challenging us to look beyond the obvious brilliance of galaxies to understand the grand, sparse architecture of everything. Within the immense silent expanse of the Bootes void, a truly remarkable phenomenon exists. the presence of a handful of galaxies. While the void is largely defined by its profound lack of luminous matter, it is not an absolute vacuum devoid of everything. Scattered throughout its vast volume are a few isolated galactic systems, often referred to by astronomers as lonely galaxies or void galaxies. These galaxies are true cosmic outliers, existing in conditions of extreme isolation that are vastly different from the crowded neighborhoods where most galaxies reside. They are like tiny islands in an unimaginably vast and empty ocean, separated by distances so great that they experience a unique cosmic existence, devoid of the constant gravitational tugs and interactions that shape their counterparts in clusters and filaments. Understanding these lonely galaxies is crucial, as they provide astronomers with a unique natural laboratory to study galaxy evolution in the absence of major external influences, offering insights that cannot be gained from galaxies in denser environments. When the Bootes void was first identified, initial surveys suggested it was almost entirely empty. However, as observational techniques improved and more detailed studies were conducted, astronomers began to detect faint signals from a small number of galaxies within its boundaries. Current estimates suggest that there are around 60 galaxies identified within the colossal volume of the Bootes void, an incredibly small number considering its immense size. To put this into perspective, if the galaxies in the universe were evenly distributed, a region the size of the Bootes void should contain thousands of galaxies, if not tens of thousands. The presence of only 60 or so spread across a volume capable of holding thousands of Milky Way-sized galaxies truly underscores their profound isolation. These galaxies are not clustered together. Rather, they are widely dispersed, often separated by tens of millions of light-years from their nearest galactic neighbour. This means that if you were standing on a planet in one of these lonely galaxies, the night sky would likely appear almost barren, with only a few faint smudges of distant light marking the presence of other void galaxies, and the truly dense parts of the cosmic web would be mere pinpricks, barely discernible if at all. The unique environment of the Bootes void likely bestows several distinct characteristics upon its lonely galaxies, setting them apart from galaxies in more crowded regions. One notable aspect is their morphology, or shape. Galaxies in dense environments frequently experience gravitational interactions, tidal forces, and even direct collisions with other galaxies. These interactions can strip away gas, trigger bursts of star formation, or distort a galaxy's shape, sometimes transforming spirals into irregular or elliptical galaxies. In contrast, the lonely galaxies in the Bootes void are largely undisturbed. They rarely, if ever, encounter another galaxy. This lack of interaction means they are less likely to undergo violent morphological transformations. As a result, many of the void galaxies identified tend to be faint spiral or irregular galaxies, often appearing more pristine and less disturbed than their counterparts in bustling clusters. Their shapes are primarily governed by their own internal dynamics, rather than external forces, making them valuable subjects for studying galaxy evolution in a relatively untouched state. Another key characteristic relates to their star formation history and gas content. Galaxies need vast reservoirs of cold gas and dust to form new stars. In dense clusters, galaxies can lose their gas through various processes such as ram pressure stripping, where hot gas in the cluster sweeps away a galaxy's own gas as it moves through the cluster, effectively starving it of star-forming material. This can lead to galaxies and clusters becoming red and dead, meaning they are older, redder, and no longer forming many new stars. Lonely galaxies in the Bootes void, however, are largely immune to such environmental stripping. They retain their gas much more effectively because there is no hot, dense, intergalactic medium to strip it away, nor are there frequent gravitational encounters to expel it. As a result, many void galaxies tend to have a more continuous and slower rate of star formation, compared to galaxies that experience bursts of star formation, triggered by mergers or interactions in denser environments. They might also appear bluer, indicating a younger, more active stellar population relative to the older, redder galaxies found in the cores of clusters. They are like quiet factories, steadily producing stars over long periods, without the dramatic surges seen in more active galactic settings. Studying these lonely galaxies presents formidable challenges for astronomers, primarily due to their extreme isolation and inherent faintness. Firstly, their vast distances from Earth, combined with their often intrinsically fainter appearance, due to their more subdued star formation rates, means that their light is incredibly faint by the time it reaches our telescopes. Gathering enough photons to create a detailed spectrum or image requires exceptionally long exposure times on the most powerful telescopes available, both on Earth and in space. This limited availability of telescope time makes each observation a precious commodity. Secondly, the very isolation that makes them unique also makes them difficult to study. In denser regions, astronomers can often use the light from brighter, nearby galaxies as reference points, or to study gravitational lensing effects. In a void, there are no such convenient neighbours. Each lonely galaxy must be observed almost entirely on its own merits, without the context of a surrounding cluster or filament. Furthermore, the limited sample size of identified void galaxies poses a significant challenge for statistical analysis. With only around 60 known galaxies within the Bhuta's void, it is difficult to draw broad statistical conclusions about their properties. While these few examples provide valuable insights, it is hard to say whether they are truly representative of all void galaxies, or if there are other types that we simply haven't been able to detect yet. The faintness also means that many smaller, fainter void galaxies might still be entirely undetectable with current technology, leading to a biased sample that favours brighter, larger systems. Despite these difficulties, astronomers painstakingly gather data on these objects, using sophisticated techniques to extract as much information as possible from their faint light signals. This involves everything from precise redshift measurements to determine their exact distances within the void, to analysing their spectral lines to understand their composition, star formation history, and internal motions. Despite the challenges, the study of lonely galaxies offers invaluable insights into fundamental questions about galaxy formation and evolution. They act as natural control groups for galaxies in denser environments. By comparing the properties of void galaxies to those in clusters and filaments, astronomers can disentangle the effects of a galaxy's internal processes from the influence of its environment. For example, if a galaxy in a cluster shows signs of having lost its gas and stopped forming stars, comparing it to a similar galaxy in a void that has retained its gas and continues to form stars can help confirm that environmental factors like ram pressure stripping are indeed responsible for the differences. This allows scientists to build more accurate models of how galaxies grow and change over cosmic time under different conditions. Lonely galaxies also provide a unique window into the initial conditions of the universe. Because they are less disturbed by mergers and interactions, they may retain more of the original characteristics from when they first formed, offering clues about the very early stages of galaxy assembly in regions of low matter density. Looking ahead, new generations of telescopes and observational surveys promise to revolutionize our understanding of lonely galaxies. Space telescopes like the James Webb Space Telescope, with its unparalleled sensitivity to infrared light, are capable of detecting much fainter and more distant objects than ever before. Future large ground-based telescopes, equipped with adaptive optics and highly sensitive instruments, will also be crucial. These advanced observatories will allow astronomers to detect more void galaxies, including potentially fainter and smaller ones, expanding the sample size and providing a more complete picture of their properties. They will also enable more detailed studies of their gas content, internal structure, and star formation processes, shedding further light on how galaxies evolve in isolation. The ability to probe deeper into the voids will not only uncover more lonely galaxies, but also help refine our models of the cosmic web and the underlying physics that governs its formation. Finally, one cannot help but ponder the cosmic view from within a lonely galaxy. For any hypothetical intelligent life residing on a planet in such a system, the night sky would be profoundly different from our own. Our Milky Way's night sky is dominated by the band of our own galaxy, studded with countless individual stars and clusters. From a lonely galaxy in the Bhuta's void, the Milky Way would be an unseen, unimaginably distant object. Instead, the sky would be largely black, dotted only by the few, widely spaced stars within their own galaxy, and perhaps, with powerful instruments, the incredibly faint pinpricks of light from other lonely galaxies hundreds of millions of light years away. This extreme isolation would likely shape their understanding of the universe in unique ways, perhaps leading them to believe their galaxy was truly alone in an endless void, ignorant of the vast cosmic web of billions of galaxies that lies far beyond their sparse reach. The very existence of these lonely galaxies serves as a powerful reminder of the universe's incredible diversity, where life, if it exists, could experience a cosmic reality that is starkly different depending on its galactic address. For a long time, our view of the universe was limited. We saw individual stars, then realized they belonged to galaxies. For a while, it was thought that galaxies were scattered somewhat randomly across the vastness of space, perhaps like dust motes suspended in a giant dark room. But as our telescopes grew more powerful, and our methods for measuring cosmic distances became more precise, a different and far more intricate picture began to emerge. What astronomers discovered was not a random scattering, but a stunningly organized, interconnected structure on the very largest scales of the universe. This grand architecture, woven from galaxies and dark matter, is known as the cosmic web. It is a fundamental framework that governs where galaxies are found and where they are not, explaining the existence of the seemingly empty regions, like the Bootes void, as integral parts of this vast cosmic design. Imagine a giant three-dimensional spiderweb stretching across unimaginable distances. This is a common and helpful analogy for the cosmic web. The galaxies are not sprinkled evenly like sugar in a bowl. Instead, they are found concentrated along the strands of this web, forming long, luminous threads. Where these threads meet and cross, galaxies gather in dense knots, creating colossal cities of stars. And between these threads and knots, there are immense cavernous spaces, truly empty voids, like the holes in a cosmic sponge. This structure is not something we can directly see with a single image, as it extends far beyond what any single telescope can capture. Instead, it is revealed by meticulously mapping the positions of millions of galaxies, each observation a tiny point on a grand, invisible blueprint. When astronomers plot these galaxies on a three-dimensional chart, the intricate web-like pattern becomes clear, showing that the universe on its largest scales is organized into this vast, interconnected network. The cosmic web is made up of three main components, each playing a crucial role in its overall structure. The first of these components are the filaments. Think of these as the long, thread-like arms of the cosmic web. These are vast, elongated structures, hundreds of millions of light-years in length, where galaxies are strung out like beads on a necklace. Our own Milky Way galaxy, for instance, resides within one of these cosmic filaments, a relatively less dense part of the web. These filaments are like the cosmic highways, guiding the flow of matter and galaxies towards the denser regions. They are not perfectly straight or uniform. Rather, they are complex, sometimes branching and twisting, reflecting the gravitational pulls that have shaped them over cosmic time. Along these filaments, galaxies exist in groups and smaller clusters, constantly moving, drawn by the gravity of the larger structures. The sheer length of these filaments is awe-inspiring. They can span distances so vast that light would take hundreds of millions of years to travel from one end to the other. They represent the skeletal framework of the universe, channeling matter and marking the paths along which galaxies have evolved and congregated. The discovery and mapping of these filaments, stretching across immense cosmic distances, was a pivotal step in understanding the true nature of the cosmic web. The second key components of the cosmic web are the clusters or nodes. These are the densest parts of the web, the places where multiple filaments intersect. Imagine where several strands of a spiderweb converge, creating a thick, strong knot. That is what a galaxy cluster is like on a cosmic scale. These clusters are the largest known gravitationally bound structures in the universe. They can contain hundreds or even thousands of individual galaxies, along with vast amounts of hot gas that emits X-rays and an even greater amount of unseen dark matter. Our local group, which includes the Milky Way, is part of a larger supercluster called Laniakea, and within Laniakea are many such galaxy clusters. These clusters are like the universe's major cities, teeming with galactic activity. Here, galaxies constantly interact, sometimes merging, sometimes pulling gas from each other, and evolving rapidly due to their crowded environments. The gravitational pull within these clusters is immense, drawing in galaxies from the surrounding filaments. These nodes are the points of highest density in the cosmic web, acting as cosmic gravitational anchors that draw matter from vast surrounding regions. Their sheer mass is mind-boggling, holding together billions upon billions of stars within a relatively compact region, even if that region still spans millions of light years. The existence of these dense knots perfectly complements the voids, showing the extreme range of matter distribution in the cosmos. And finally, the third and perhaps most mysterious components of the cosmic web are the voids. These are the vast, relatively empty spaces that lie between the filaments and clusters. They are the holes in the cosmic sponge, the areas where matter, particularly luminous matter like galaxies, is incredibly sparse. The Bootes void is a prime example of such a region, a gigantic bubble of emptiness in the cosmic fabric. These voids are not simply regions where there happens to be a gap. They are actively expanding, growing emptier over time as the matter around them is pulled into the denser filaments and clusters by gravity, and as the universe itself expands, stretching the already sparse matter even further apart. Voids can span hundreds of millions of light years, and inside them, the density of ordinary matter is incredibly low, often less than 1/10 of the average cosmic density. While not entirely empty of every single atom, they are profoundly lacking in the galaxies, stars, and nebulae that characterize the rest of the cosmic web. They are the silent regions of the universe, where starlight is scarce and cosmic interactions are rare, highlighting the profound isolation of any galaxy that happens to reside within their boundaries. The question of how voids like Bootes fit into this grand cosmic architecture is central to understanding the cosmic web. Voids are not just random empty spaces that happen to exist. They are an intrinsic and necessary part of the web's formation. They are the spaces left behind as gravity pulls matter into the filaments and clusters. Imagine pulling on a piece of stretchy fabric. As you pull one part, other parts naturally thin out and become empty. A similar process occurs in the universe. Where matter clumps together to form the dense parts of the web, it naturally leaves vast underdense regions in between. The Bootes void is a colossal testament to this process. It is a region where the initial conditions of the early universe, combined with the relentless work of gravity and the expansion of space, led to a profound lack of matter. It is essentially a giant bubble, bounded by the surrounding filaments of galaxies, which act as its walls. These walls are not distinct physical barriers, but rather simply the denser regions where galaxies have preferentially clumped. So the Bootes void is not outside the cosmic web. It is a fundamental and defining feature of the web itself, an enormous gap within the network, perfectly illustrating the extreme variations in matter density that characterize the universe on its largest scales. Its very existence highlights the foam-like or sponge-like nature of cosmic structure, where concentrated matter forms the spongy material, and the voids are the empty spaces within the sponge. Our own place in this cosmic web helps to contextualize the Bootes void. As mentioned, our Milky Way galaxy is part of the local group, which in turn is a member of the Laniakea supercluster. The Laniakea supercluster itself is a vast filamentary structure, a kind of cosmic continent of galaxies. We are not located in a void, but rather within a relatively dense part of the cosmic web, a filament that is slowly being drawn towards the denser gravitational center of the Laniakea supercluster. The Bootes void lies far beyond our immediate supercluster, hundreds of millions of light years away, in a different part of the cosmic geography. It serves as a stark reminder of the immense scale and diverse environments that exist within the universe, ranging from the crowded galactic cities to the vast, empty cosmic deserts. Understanding our own position within this web helps us to better comprehend the scale and significance of structures like the Bootes void, which represent a different, equally important aspect of the universe's grand architecture. The existence and structure of the cosmic web are not just theoretical constructs. They are supported by a wealth of observational evidence. Modern astronomy, particularly through large-scale galaxy redshift surveys, has allowed scientists to meticulously map the three-dimensional positions of millions of galaxies. By measuring the redshift of light from countless galaxies across vast regions of space, astronomers can calculate their distances and plot them in a three-dimensional map. When these maps are created, the cosmic web emerges with striking clarity. The filaments are visible as long, interconnected chains of galaxies, the clusters appear as dense knots where these chains intersect, and the voids are plainly visible as enormous regions where galaxies are almost entirely absent. These observational maps provide compelling visual confirmation of the theoretical predictions about the universe's large-scale structure. The Bootes void itself was one of the earliest and most dramatic pieces of evidence for the cosmic web, revealing an unexpectedly large and well-defined emptiness that solidified the idea of a structured, non-uniform universe. These detailed maps continue to be refined with newer, more powerful telescopes, providing ever clearer images of the universe's grand, web-like architecture, and continually reinforcing the idea that voids are fundamental components of this cosmic scaffolding. The cosmic web is therefore not just a beautiful picture, it is a scientifically confirmed reality that defines the universe on its largest scales, with voids like Bootes playing a central role in its intricate design. Topic: How voids form. The universe we observe today is a place of immense structure and diversity. From tiny atoms to gigantic galaxy clusters, matter is arranged in complex patterns. But this was not always the case. In the very earliest moments after the Big Bang, the universe was incredibly hot and dense, and importantly, it was remarkably smooth and uniform. Imagine a perfectly blended cosmic soup, with matter and energy distributed almost perfectly evenly throughout. So, how did this smooth, uniform soup transform into the lumpy web-like structure we see today, with dense clusters of galaxies separated by vast empty voids like the one in Bootes? This is one of the most fundamental questions in cosmology, and the answer lies in the interplay of incredibly tiny initial differences, the relentless pull of gravity, and the continuous expansion of space over billions of years. The formation of cosmic voids, including the immense Bootes void, is a direct and expected outcome of these fundamental processes. The story of how voids form begins with what scientists call initial tiny differences, or primordial fluctuations. Despite the early universe being incredibly uniform, it was not perfectly so. Quantum mechanics, the theory that governs the behavior of matter at the smallest scales, predicts that even in a seemingly smooth early universe, there would have been minuscule, unavoidable fluctuations in density and temperature. These were not large variations, but incredibly small, microscopic ripples in the cosmic soup, like imperceptible bumps and dips in an otherwise flat surface. These fluctuations are thought to have arisen from quantum processes in the very first moments of the Big Bang, when the universe was smaller than an atom. As the universe expanded rapidly from this extremely tiny state, these quantum fluctuations were stretched and magnified to astronomical scales, becoming the subtle seeds from which all future cosmic structures would grow. Some regions ended up with a tiny bit more matter than average, and some with a tiny bit less. These almost imperceptible variations, barely noticeable at first, were the crucial starting points for everything we see today, including the vast emptiness of voids. The primary sculpture of the universe's structure, acting upon these tiny initial differences, is gravity. Gravity is the fundamental force that attracts objects with mass or energy towards each other. Its strength depends on the amount of mass involved and the distance between objects. In the early universe, even though the density differences were tiny, gravity immediately began to work on them. In the regions where there was a slightly higher concentration of matter, gravity exerted a slightly stronger pull. This stronger pull began to draw in even more matter from the surrounding areas, slowly, imperceptibly at first, but relentlessly. Conversely, in the regions where there was slightly less matter than average, gravity's pull was weaker. As surrounding matter was drawn away to the denser regions, these underdense areas were gradually depleted, becoming even emptier. It is a snowball effect, but in reverse for the voids. The rich get richer in terms of matter density, and the poor get poorer. Gravity acts as a cosmic vacuum cleaner, sucking matter away from the underdense regions and piling it up in the overdense ones. This process of small differences growing larger over time is known as gravitational instability. It is a fundamental concept in cosmology, explaining the growth of structures in the universe. Imagine a perfectly balanced house of cards. If you introduce even a tiny, almost imperceptible tremor, the instability grows and the cards eventually collapse. In the cosmic context, the tiny initial density fluctuations were like those tremors. Over billions of years, gravity continuously amplified these small differences. Regions that were slightly denser began to collapse inward, drawing in more and more gas and dark matter. These regions eventually grew into the cosmic filaments and galaxy clusters we observe today, the luminous threads and knots of the cosmic web. At the same time, the regions that were initially slightly underdense began to expand more rapidly than the average universe. As matter was pulled away from them towards the growing denser regions, they became even more underdense. They were effectively emptied out by the gravitational pull of their denser neighbours. The gaps between the growing clusters and filaments widened and deepened, forming the vast cosmic voids. This is the core mechanism behind void formation. The universe is matter sorting itself out due to its own gravity, creating a dichotomy of crowded and empty spaces. A crucial, often unseen player in this cosmic sorting process is dark matter. Dark matter is a mysterious substance that does not interact with light or other forms of electromagnetic radiation, meaning we cannot see it directly. However, we know it exists because of its powerful gravitational effects. Scientists believe that dark matter makes up about 85% of all matter in the universe, far outweighing the ordinary matter that makes up stars, planets, and everything we can see. Because dark matter is so much more abundant, it provided the primary gravitational scaffolding around which ordinary matter could clump. In the early universe, it was the slight overdensities of dark matter that first began to gravitationally pull in more dark matter and, crucially, also ordinary matter. These initial clumps of dark matter formed the gravitational seeds for galaxies and clusters. Similarly, the initial underdensities of dark matter laid the groundwork for the voids. While voids are incredibly sparse in ordinary matter, they still contain a significant amount of dark matter, albeit at a lower density than the filaments and clusters. Dark matter's gravitational influence is what largely dictated where the initial structures would form and where the voids would be left behind. Its dominant gravitational role means that it effectively sets the stage for the distribution of visible galaxies. Beyond gravity, another powerful force influencing void formation is the cosmic expansion. The universe is not static. It has been continuously expanding since the Big Bang. This expansion means that the space between galaxies is constantly stretching, making the universe bigger over time. This expansion plays a dual role in structure formation. On small scales, within galaxies and clusters, gravity is strong enough to overcome the expansion and pull matter together. But on very large scales, the expansion of space is a dominant force. In the regions that were already slightly underdense, the future voids, the expansion of space further contributes to their emptiness. As the space within these voids stretches, the already sparse matter within them is pulled even further apart. This effect is sometimes referred to as cosmic dilution. The universal expansion effectively accelerates the emptying process within voids. It is like blowing up a balloon with dots on it. The dots that are already far apart get even further apart as the balloon inflates. This constant stretching of space ensures that voids continue to grow and become even emptier over cosmic time, making them a direct consequence of the universe's dynamic expansion. The formation of voids, along with the entire cosmic web, is a complex process that unfolds over billions of years. To understand it fully, scientists rely heavily on computer simulations. These simulations are like virtual universes, starting with the conditions of the early universe, the tiny density fluctuations, the mix of ordinary and dark matter and the expanding space. Scientists then let the simulation run, allowing gravity and cosmic expansion to act on the matter over cosmic timescales. These simulations consistently show that the initial tiny fluctuations, under the influence of gravity and expansion, naturally evolve into a cosmic web structure, complete with filaments, clusters, and vast voids strikingly similar to what we observe in the real universe. The Bootes void, with its exceptional size and emptiness, is a prime example of a structure that naturally arises from these theoretical models. These simulations are incredibly powerful tools because they allow cosmologists to test different assumptions about the early universe and the properties of dark matter and dark energy, seeing how those changes affect the final structure of the cosmic web and the characteristics of the voids that form. They provide a dynamic visual representation of how emptiness is born from tiny beginnings. Finally, observations of voids like booties are crucial for confirming and refining these theoretical models of structure formation. By carefully mapping the distribution of galaxies, measuring their distances, and studying the properties of the few galaxies that reside within voids, astronomers can gather data that directly supports the idea that voids formed from gravitational instability acting on primordial fluctuations. The sheer size and profound emptiness of the Boot's void, in particular, provides strong evidence for the effectiveness of this process. Its existence and characteristics are not anomalous. Rather, they're a natural and expected outcome of the universe's fundamental laws, acting over immense periods of time and across unimaginably vast scales. The study of how voids form, therefore, is not just about understanding empty spaces. It is about understanding the very essence of how our universe transformed from a nearly uniform beginning into the grand, structured, and often surprisingly empty cosmos we inhabit today. The Booty's void serves as a monumental, silent testament to the universe's fundamental laws of physics at play on the grandest scales. The universe, as we perceive it, is filled with the radiant glow of stars and galaxies, the visible manifestations of ordinary matter. This ordinary matter, made of atoms like hydrogen, helium, and all the elements that compose planets, people, and everything we can touch and see, is what our telescopes directly detect. However, modern cosmology, our study of the universe as a whole, has revealed a profound and surprising truth. The visible universe, the luminous one, is but a small fraction of the total cosmic inventory. The vast majority of matter in the cosmos is not the familiar stuff of stars and planets. It is something invisible, mysterious, and utterly dominant in shaping the universe's grand architecture. This unseen substance is known as dark matter, and its role in the formation and evolution of cosmic structures, including the immense empty regions like the Booty's void, is absolutely fundamental. Without the gravitational influence of dark matter, the universe as we know it, with its intricate cosmic web of galaxies and vast empty spaces, simply would not exist. It is the silent, unseen sculptor that has moulded the cosmos into its present form, influencing where galaxies gather and where they are conspicuously absent. We cannot directly see dark matter because it does not interact with light or any other form of electromagnetic radiation. It does not absorb, reflect, or emit light, making it effectively transparent to our telescopes. This is why it is called dark, yet its presence is undeniable, inferred through its powerful gravitational pull on visible matter. We observe galaxies spinning much faster than their visible stars and gas alone could account for, suggesting an enormous unseen mass holding them together. We see light from distant objects bending around galaxy clusters in ways that can only be explained by far more mass than is visible, and, perhaps most compellingly for the large-scale structure, we see the universe's cosmic web, with its filaments, clusters and voids, form in a way that is only possible if dark matter provides the gravitational scaffolding. Scientists estimate that dark matter constitutes about 85% of all matter in the universe. This means that for every handful of ordinary matter, there are 5 or 6 handfuls of dark matter silently pulling and shaping the cosmos. Its overwhelming abundance compared to ordinary matter makes it the primary gravitational driver of cosmic evolution on the larger scales. The story of how voids, and indeed all large-scale structures, formed begins with the very early universe, shortly after the Big Bang. In those nascent moments, the universe was incredibly hot and dense, and largely uniform. However, it was not perfectly smooth. There were tiny, microscopic fluctuations in density, regions where the concentration of matter was ever so slightly higher or lower than the average. These primordial fluctuations, thought to have originated from quantum processes in the universe's infancy, were the seeds for all future cosmic structures. Crucially, these initial tiny differences were present in both ordinary matter and dark matter. Because dark matter makes up so much more of the universe's total mass, the fluctuations in dark matter density had a much more significant gravitational impact. Where there was a tiny bit more dark matter, its gravity would exert a slightly stronger pull. Where there was a tiny bit less dark matter, its gravitational influence would be correspondingly weaker. These minuscule initial variations in dark matter density were the true architects of the cosmic web. Over billions of years, gravity began its relentless work on these initial slight differences. In regions where there was a slightly higher concentration of dark matter, its collective gravity started to pull in even more dark matter, as well as the ordinary matter, gas and dust from the surrounding areas. These overdense regions began to grow, slowly accumulating more and more mass. This process is known as gravitational instability. Small clumps grow larger by attracting more material. These growing clumps of dark matter formed invisible halos, or wells, into which ordinary matter would eventually fall. Imagine these dark matter halos as invisible gravitational mountains. As gas and dust from the early universe drifted through space, they would be drawn into these gravitational wells, eventually cooling, clumping, and forming the first stars and then the first galaxies. The galaxies we see today are essentially living within these much larger invisible dark matter halos, bound to them by gravity. The dark matter acts as the fundamental scaffolding, the underlying skeleton that provides the gravitational glue to hold galaxies together and to draw them into larger structures like clusters and filaments. Without this pervasive dark matter, the gravitational forces from ordinary matter alone would have been far too weak to overcome the universe's rapid expansion and form the large, well-defined galaxies and clusters we observe in the relatively short time since the Big Bang. The universe would likely be a much more uniform, diffuse soup of gas, with very few, if any, large coherent structures. Conversely, the role of dark matter is equally critical, though perhaps less intuitive, in the formation of cosmic voids like the Bootes void. Just as there were regions with slightly more dark matter, there were also regions with slightly less dark matter than the cosmic average. These were the initial underdensities. In these sparse regions, the collective gravitational pull of dark matter was weaker, as matter, both dark and ordinary, was drawn towards the neighbouring regions of higher dark matter density. These underdense areas were actively emptied out. Think of it as a cosmic drainage system. The denser regions, driven by the stronger gravitational pull of their higher dark matter concentrations, act like gravitational sinks, drawing matter away from the surrounding less dense areas. The matter in the proto-voids, having less dark matter to exert a gravitational pull, was unable to hold on to its material as effectively. Instead, it was slowly but surely pulled towards the growing filaments and clusters. This process of matter flowing away from underdense regions and accumulating in overdense ones is what sculpts the cosmic web, leaving behind the vast empty spaces we call voids. The Bootes void, being one of the largest voids, represents an area that was initially significantly underdense in dark matter, leading to a profound absence of both dark matter and consequently ordinary matter as time progressed. Even within the heart of a cosmic void, such as the Bootes void, dark matter is still present, albeit at a much lower density than the cosmic average. It is not completely devoid of dark matter, just remarkably sparse. The distribution of dark matter within a void is likely more diffuse and less clumped than in filaments or clusters. This lower density of dark matter means that the local gravitational fields within the void are significantly weaker. This has important implications for the few lonely galaxies that reside within the Bootes void, because these galaxies are not bathed in a strong, clumpy dark matter halo of a cluster, and are far from the strong gravitational influences of galactic filaments. Their evolution is less affected by external gravitational interactions. Their own internal dark matter halos, though isolated, still play a crucial role in binding their stars and gas, but the cosmic environment around them is one of profound gravitational calm. The dark matter in the void ensures that even these seemingly empty regions are still subject to the subtle, large-scale gravitational forces that continue to shape the universe, albeit in a more gentle, expansive manner. The impact of dark matter's role can also be seen in the very structure of the cosmic web itself. The filaments and clusters are not just collections of galaxies, they're embedded within massive invisible networks of dark matter. These dark matter structures are much more expansive and diffuse than the visible galaxies they host. The voids, conversely, are regions where these dark matter structures are either absent or incredibly sparse. Computer simulations, which model the evolution of the universe from its early moments, consistently show that the large-scale structure we observe, with its distinct web-like pattern of filaments, clusters and voids, only emerges when dark matter is included in the calculations. If simulations are run with only ordinary matter, the gravitational forces are simply too weak to form such pronounced structures in the time available since the Big Bang. The universe would be far more uniform, lacking the dramatic variations in density that characterize the cosmic web and its colossal voids. This strong agreement between theoretical simulations, including dark matter, and actual astronomical observations of the cosmic web, provides some of the most compelling evidence for dark matter's existence and its indispensable role in shaping the universe. The very existence of giant holes like the Booty's void serves as a powerful, indirect confirmation of dark matter's profound gravitational influence, demonstrating its ability to create not only concentrations of matter, but also vast regions of cosmic emptiness by drawing matter away. It is the unseen architect, defining the presence and the absence of light in the vast cosmic landscape. The study of voids thus becomes an indirect window into the properties of dark matter, allowing us to understand how this mysterious substance sculpted the large-scale universe and created the grand, often empty tapestry of space. Just as dark matter plays a silent yet dominant role in structuring the universe, another mysterious component, dark energy, exerts a profound and equally pervasive influence, particularly on the expansion of space itself and the growth of the universe's emptiest regions, the cosmic voids. While dark matter is about clumping things together through gravity, dark energy is about pushing things apart, accelerating the universe's expansion. This subtle, yet powerful force was an entirely unexpected discovery, fundamentally changing our understanding of the cosmos and providing a new lens through which to view the evolution of structures like the Booty's void. Its uniform presence throughout the universe means that its effects become most evident precisely where ordinary matter and dark matter are thinnest, making voids an ideal laboratory for studying this enigmatic force. The story of dark energy begins in the late 1990s, when two independent teams of astronomers were studying distant supernovae, which are powerful exploding stars. These supernovae act as standard candles, meaning astronomers can use their known intrinsic brightness to determine their distances from Earth. By measuring the redshift of the light from these supernovae, scientists can also determine how fast the galaxies containing them are moving away from us. The expectation was that the expansion of the universe, initiated by the Big Bang, should be slowing down due to the gravitational pull of all the matter within it. It was like throwing a ball into the air. You expect it to slow down as gravity pulls it back. However, to the astonishment of the scientific community, the observations showed the opposite. The distant supernova were fainter than expected, meaning they were farther away than they should be if the universe's expansion were merely slowing down. This implied that the universe's expansion was not only continuing, but it was actually speeding up or accelerating. This groundbreaking discovery led to the hypothesis of dark energy, a mysterious force responsible for this accelerated expansion. Unlike dark matter, which clumps together due to gravity, dark energy is thought to be a smoothly distributed component, pervasive throughout all of space. It is not concentrated in galaxies or clusters. Instead, it is uniformly spread, meaning there is an equal amount of dark energy in every cubic meter of space, whether that space is in the middle of a galaxy or in the deepest cosmic void. This uniform distribution is a key characteristic that differentiates it from matter, both ordinary and dark, which is concentrated in the cosmic web. Dark energy acts as a kind of anti-gravity, a repulsive force that pushes space apart, causing the universe to expand at an ever-increasing rate. Its effect becomes more pronounced as the universe gets larger and less dense, because the gravitational pull of matter, which works to slow expansion, becomes relatively weaker over vast distances, allowing dark energy to dominate. The impact of dark energy on the universe's structure, and specifically on the growth of voids, is profound. In regions where matter is highly concentrated, such as galaxy clusters and filaments, the gravitational pull of ordinary and dark matter is very strong. This strong gravity acts to pull matter together, overcoming the expansive push of dark energy and the general expansion of the universe. This is why clusters remain bound, and galaxies within them continue to interact and merge. In these dense environments, dark energy's effect is still present, but its repulsive push is largely masked or dominated by the overwhelming gravitational attraction of the concentrated matter. However, the situation is dramatically different within cosmic voids, such as the Bootes void. These regions, by their very definition, are extremely sparse in both ordinary and dark matter. The gravitational pull exerted by the meagre amount of matter within a void is exceptionally weak. In these underdense environments, the uniform repulsive force of dark energy becomes the dominant influence. There is simply not enough matter in a void to exert a strong enough gravitational pull to counteract dark energy's push. As a result, voids are not just expanding along with the rest of the universe, they are expanding faster than the universe as a whole in their local regions. The cosmic expansion is like stretching a rubber sheet. If you have dense knots on the sheet, they resist the stretching, but in the empty spaces between the knots, the sheet stretches more easily and more rapidly. Similarly, voids are the parts of the cosmic web that are being most effectively stretched by dark energy. They are growing emptier and larger at an accelerating rate because there is little local gravity to hold them back. This makes cosmic voids incredibly important laboratories for studying dark energy. Because the gravitational effects of matter are minimized within voids, they provide a cleaner environment to observe the subtle yet powerful influence of dark energy. By studying the precise sizes, shapes, and expansion rates of voids, astronomers can gather crucial data to test different theories about the nature of dark energy. For example, if dark energy truly is a constant, uniformly distributed force, like Einstein's cosmological constant, then voids should expand in a predictable way. If dark energy changes over time or varies in density, then the expansion of voids might show different patterns. Measuring how quickly voids empty out and expand, and how the few galaxies within them behave, provides direct observational constraints on the properties of dark energy, helping scientists to understand its fundamental nature and its role in the universe's destiny. The Bootes void, being one of the largest and most well-studied voids, is particularly valuable in this regard, offering a massive region where dark energy's expansive push is expected to be profoundly evident. The accelerating expansion driven by dark energy has profound implications for the very long-term future of the universe and its structures, including voids. As dark energy continues to dominate, the universe will expand at an ever-increasing pace. This means that galaxies that are not gravitationally bound to each other, like those in different galaxy clusters, will move farther and farther apart, eventually receding beyond our observable horizon. The cosmic web, which currently connects galaxies through filaments, will become increasingly stretched and attenuated. Filaments will grow thinner, and the connections between clusters will weaken and break. The voids, already sparse, will become even more incredibly empty. Over vast timescales, billions and trillions of years into the future, the universe might become a lonely place, where each galaxy or small gravitationally bound group of galaxies is an isolated island, completely unaware of other galaxies due to their extreme recession speeds. Light from these distant galaxies would be so redshifted that it would become undetectable, effectively making them vanish from our view. The voids would then represent the ultimate expression of this accelerating expansion, vast regions where nothing but increasingly stretched out space remains between isolated, dying galaxies. Trying to measure something as immense and as empty as the Bootes void might seem like a nearly impossible task. It is not like measuring a table with a ruler, or even a planet with satellites. The Bootes void is a truly gigantic hole in the universe, an area defined by what it lacks, a significant number of galaxies. So how do astronomers, those dedicated explorers of the cosmos, go about mapping something that is mostly nothing? The answer lies in clever techniques, powerful telescopes, and a deep understanding of how light travels across the universe. It is a process that relies on indirect clues and the painstaking collection of data from the few objects that either reside within the void or delineate its vast boundaries. The entire endeavour is a testament to scientific ingenuity, building a picture of the universe's grand architecture from faint whispers of light collected over many years. The most fundamental technique for measuring and mapping cosmic voids, including the Bootes void, is through what are known as galaxy redshift surveys. Imagine trying to map a huge, invisible forest where you can only see the trees. To understand the forest, you need to know not just where each tree appears on a flat map, but also how far away each tree is from you. This allows you to build a three-dimensional picture of the forest, revealing its true depth, its clearings, and its dense groves. In cosmology, galaxies are our trees. We can see where they are on the sky, a two-dimensional view. But to understand the universe's true structure, we need their distance from us. This allows us to construct a three-dimensional map of the cosmos, revealing the threads of galaxies and the vast empty spaces between them. The process of a galaxy redshift survey begins with powerful telescopes. These are not just giant magnifying glasses. They are sophisticated instruments designed to collect the incredibly faint light from distant galaxies. Large ground-based telescopes situated in places with clear dark skies like the deserts of Chile, home to the European Southern Observatory's Very Large Telescope, or VLT, or the mountaintops of Hawaii, like the Keck Observatory, are essential. These telescopes have mirrors many meters across, designed to gather as much light as possible over long periods. Space telescopes, such as the Hubble Space Telescope or the newer James Webb Space Telescope, also play a crucial role, especially for detecting the very faintest and most distant galaxies, as they are above Earth's blurring atmosphere. These telescopes act as cosmic light buckets, collecting ancient photons that have travelled for millions or even billions of years to reach us. Once the light from a distant galaxy is collected by the telescope, it is fed into a special instrument called a spectrograph. A spectrograph is like a sophisticated prism. Instead of just bending light, it precisely splits the incoming light from the galaxy into its individual colours, much like how a rainbow is formed when sunlight passes through raindrops. But a spectrograph does this with extreme precision, creating a detailed spectrum of the galaxy's light. This spectrum is not just a smooth rainbow, it is crossed by dark and bright lines. These lines are like the unique fingerprints of elements. Every element in the universe, when heated or when light passes through it, absorbs or emits light at very specific, precise colours or wavelengths. For example, hydrogen, the most abundant element, has a very distinct pattern of lines. When astronomers look at the spectrum of a distant galaxy, they identify these familiar patterns of lines. The crucial part for mapping the void comes from observing how these fingerprint lines are shifted. If a galaxy were perfectly still relative to us, those lines would appear at exactly the same wavelengths as measured in a laboratory on Earth. However, distant galaxies are almost universally moving away from us due to the expansion of the universe. When a light source moves away from an observer, its light waves get stretched out. When light waves stretch, their wavelength becomes longer, and they shift towards the red end of the electromagnetic spectrum. This phenomenon is called redshift. The more stretched the light waves are, the more significant the redshift, and the faster the galaxy is moving away from us. By accurately measuring how much these specific spectral lines have shifted towards the red, astronomers can calculate the galaxy's redshift value. This redshift value is directly related to how fast the galaxy is receding from us, and thanks to Edwin Hubble's discovery, Hubble's law, that recession speed is directly related to the galaxy's distance. The greater the redshift, the farther away the galaxy is. This connection between redshift and distance is the universe's built-in cosmic ruler. To map a structure as large as the Bootes void, astronomers need to collect redshift information for thousands, even millions of galaxies over a vast area of the sky. This is not a quick process. Surveys like the Sloan Digital Sky Survey, SDSS, or the 2-degree field galaxy redshift survey, 2DFGRS, are massive undertakings that involve dedicated teams and years of observation. They systematically scan large patches of the sky, taking spectra for hundreds or thousands of galaxies at a time. The data collected from these surveys includes the precise position of each galaxy on the sky, its two-dimensional coordinates, and its measured redshift, which gives its distance. With these two pieces of information for countless galaxies, astronomers can then construct a three-dimensional map of the universe. On such a map, galaxies would appear as points of light, and their positions would reveal the grand structures, the long thread-like filaments of galaxies, the dense knots of galaxy clusters where filaments intersect, and, most importantly for our discussion, the vast empty regions where galaxies are conspicuously absent. Identifying the Bootes void itself within these three-dimensional maps involves a specialized form of data analysis. It is not about looking for a single, distinct boundary line, but rather for regions where the density of galaxies drops significantly below the cosmic average. Astronomers use statistical methods to analyze the distribution of galaxies in their maps. They look for large, contiguous volumes of space where the number of observed galaxies is significantly lower than what would be expected if galaxies were distributed randomly or uniformly. Imagine plotting all the galaxies as dots on a computer screen. In a normal region of the universe, the dots would be relatively dense. In a void, there would be huge empty spaces, vast patches on the screen with very few or no dots. The Bootes void stands out on these maps as a colossal hole in the galaxy distribution, a clear and dramatic underdensity. Scientists can quantify this emptiness by calculating the density contrast, which is a measure of how much sparser a void is compared to the average density of the universe. For the Bootes void, this density contrast is very high, indicating it is one of the emptiest known regions. Further analysis techniques, such as percolation analysis, are also used. This method helps to identify how large clusters of empty space are connected. Imagine pouring water over a sponge. The water flows through the holes. Percolation analysis is a way to mathematically identify and characterize these large, connected empty regions within the cosmic web. It helps astronomers to trace the boundaries of the void, even though these boundaries are fuzzy and not sharply defined. The edges of the Bootes void are not solid walls, but rather regions where the galaxy density gradually increases to meet the surrounding filaments and clusters of the cosmic web. The void is essentially a gigantic bubble, defined by the denser galactic structures that surround it, almost like an empty space left behind as matter gravitated towards the walls of the cosmic web. A particularly challenging yet incredibly important aspect of measuring the Bootes void is studying the few galaxies within it. These are the lonely galaxies discussed in a previous chapter. Their very existence confirms that the void is not absolutely empty, but rather profoundly underdense. Observing these galaxies is exceptionally difficult because they are both very distant and often intrinsically faint, as they are not undergoing the same vigorous star formation as galaxies in crowded environments. This requires even longer exposure times and the use of the most sensitive detectors. By measuring the redshift of these lonely galaxies, astronomers can confirm that they are indeed located within the distance range of the Bootes void, not just foreground or background objects seen in the same direction. Furthermore, by analysing the light from these isolated galaxies, scientists can study their properties, their shapes, star formation rates, and gas content to understand how galaxies evolve in a truly isolated, gravitationally calm environment, free from the strong interactions that dominate in denser parts of the universe. These lonely galaxies act as crucial probes, helping us understand the void's internal environment and its unique influence on galactic evolution. Looking to the future, new technologies and observational programs promise even more precise measurements of the Bootes void and other cosmic structures. Next-generation large-scale galaxy surveys, with wider fields of view and greater sensitivity, will map millions more galaxies, pushing the boundaries of our three-dimensional cosmic maps. Instruments capable of observing fainter light and across broader wavelengths, like infrared light, which can penetrate cosmic dust, will help uncover even more distant and previously hidden galaxies, including potentially more within the voids. Advanced computational methods and artificial intelligence are also being developed to process the enormous datasets generated by these surveys, making it easier to identify and characterize voids and the intricate patterns of the cosmic web. Even subtle clues from the cosmic microwave background, CMB, the leftover radiation from the Big Bang, can provide insights into voids. As the CMB photons travel across the universe, their path is slightly affected by the gravitational fields of the structures they encounter. When CMB photons pass through a large cosmic void, they experience a slight cold spot, or dip in temperature compared to photons passing through denser regions. This is due to a subtle effect known as the integrated Sachs-Wolf (ISW) effect. While incredibly faint and challenging to detect, these cold spots on the CMB map can sometimes correspond to the presence of large cosmic voids, offering another independent way to confirm their existence and study their properties. Although not a direct measurement of the void's boundaries, it provides supporting evidence of its large-scale gravitational impact. The measurement of the Boots void, therefore, is not a simple direct observation but a sophisticated scientific detective story. It involves collecting incredibly faint light from millions of distant galaxies, painstakingly measuring their redshifts to determine their three-dimensional positions, and then using powerful statistical tools to reveal the grand, sponge-like structure of the universe with its filaments, clusters, and vast empty holes. It is a continuous process of refining our cosmic maps, pushing the boundaries of our observational capabilities, and deepening our understanding of how the universe is put together on its very grandest scales, revealing that even the absence of matter can tell us a profound story about the cosmos. The ongoing work to measure and understand voids like Booties is a testament to humanity's relentless quest to map the unknown and decipher the universe's deepest secrets. Imagine you are standing beside a railway track and a train approaches with its horn blaring. As the train comes closer, the pitch of the horn sounds higher. Then, as the train passes you and speeds away into the distance, the pitch of its horn suddenly drops and sounds lower. This change in the pitch of a sound wave caused by the motion of its source relative to an observer is a common experience we call the Doppler effect. The sound waves are compressed as the source approaches, making the wavelength shorter and the pitch higher, and they are stretched out as the source recedes, making the wavelength longer and the pitch lower. This everyday phenomenon with sound has a direct and incredibly powerful parallel in the universe, but instead of sound waves, it involves light waves. This is the concept of redshift, a cornerstone of modern astronomy and cosmology, and the primary tool used to measure the vast distances to galaxies and map the universe's grand structure, including the immense empty regions like the Booties void. To understand redshift, we first need to briefly think about light. Light travels as waves, much like ripples on a pond. The colour of light depends on its wavelength, the distance between two consecutive peaks of the wave. For example, red light has a longer wavelength than blue light. The entire range of possible wavelengths of light, from very long radio waves to very short gamma rays, is called the electromagnetic spectrum. Our eyes can only see a tiny portion of this spectrum, which we call visible light, encompassing the colours of the rainbow from red, longer wavelengths, to violet, shorter wavelengths. Now, apply the Doppler effect idea to light. When an object that emits light, like a star or a galaxy, is moving away from us, the light waves it emits get stretched out during their journey. As these light waves stretch, their wavelengths become longer. In the visible part of the spectrum, longer wavelengths correspond to the red end of the rainbow. So if a galaxy is moving away from us, the light we receive from it will appear shifted towards the redder colours. This is called redshift. Conversely, if an object were moving towards us, which is rare for distant galaxies due to the universe's expansion, but happens for nearby ones like the Andromeda Galaxy, its light waves would be compressed, their wavelengths would become shorter, and they would appear shifted towards the bluer end of the spectrum. This is called blue shift. For the vast majority of distant galaxies, however, we observe redshift because they are moving away from us due to the expansion of space. For distant galaxies, the redshift we observe is not primarily due to the galaxy moving through space, like our train analogy. Instead, it is mostly due to the expansion of space itself. Imagine drawing dots on the surface of a deflated balloon. As you inflate the balloon, the surface stretches, and the distance between any two dots increases. The dots themselves are not moving across the surface of the balloon. The surface itself is expanding. Similarly, in the universe, the space between galaxies is expanding, stretching the light waves as they travel from the distant galaxy to our telescopes. This is called cosmological redshift, and it is the dominant form of redshift for galaxies billions of light-years away. It is a direct consequence of the universe's continuous expansion since the Big Bang. The further away a galaxy is, the longer its light has been travelling through expanding space, and therefore the more its light waves have been stretched, resulting in a greater observed redshift. How do astronomers actually measure this redshift? They use a special instrument called a spectrograph, which we briefly mentioned in the previous chapter. When light from a distant galaxy enters a telescope, it is fed into this spectrograph. The spectrograph spreads the galaxy's light into its component colours, creating a detailed spectrum. On this spectrum, astronomers look for specific patterns of spectral lines. These lines are like unique barcodes or fingerprints that identify particular chemical elements present in the galaxy. For instance, hydrogen atoms, under certain conditions, will absorb or emit light at very specific known wavelengths. We know exactly what these patterns look like when measured in a laboratory on Earth. When astronomers observe the spectrum of a distant galaxy, they compare the pattern of its spectral lines to the known patterns of elements in the laboratory. If the galaxy is receding from us, all of its spectral lines will be shifted towards the red end of the spectrum by the exact same proportion. It is like taking a well-known song, but all the notes are played a little bit lower by a consistent amount. The astronomers then measure precisely how much these lines have shifted. The amount of this shift is quantified by a number called the redshift parameter, usually denoted by the letter Z. A higher Z value means a greater redshift, which in turn means the light has been stretched more, indicating the galaxy is moving away faster and is farther away. The groundbreaking connection between redshift and cosmic distance was established by the American astronomer Edwin Hubble in the late 1920s. Hubble observed that almost all galaxies outside our local group were moving away from us, and critically, the farther away a galaxy was, the faster it appeared to be receding. This remarkable relationship is known as Hubble's law. It states that a galaxy's recession velocity, how fast it is moving away from us, is directly proportional to its distance from us. In simple terms, if a galaxy is twice as far away, it will be moving away from us twice as fast and its light will be twice as redshifted. This law effectively turned redshift into the universe's most powerful distance measuring tool for objects beyond our immediate galactic neighbourhood. Before Hubble's law, measuring distances to galaxies was incredibly difficult and uncertain, limiting our understanding of the universe's true scale. With redshift, astronomers suddenly had a reliable cosmic yardstick. The significance of redshift extends beyond just measuring distance. It also acts as a kind of cosmic time machine. Because light travels at a finite speed, it takes time for light from distant objects to reach us. The farther away an object is, the longer its light has been travelling. Therefore, when we observe a galaxy with a high redshift, we are not seeing it as it is today, but as it was billions of years ago, when the light left it. A galaxy with a redshift of, say, 1 means its light has travelled for roughly 7 to 8 billion years to reach us, showing us the galaxy as it was when the universe was about half its current age. Galaxies with even higher redshifts, for example Z equals 8 or 10, are incredibly distant, and their light has travelled for so long that we're seeing them as they were just a few 100 million years after the Big Bang, providing glimpses into the very early universe when the first stars and galaxies were just beginning to form. Redshift thus allows astronomers to peer back into cosmic history, observing the universe at different epochs and studying how galaxies and structures have evolved over billions of years. Redshift is absolutely crucial for mapping the large-scale structure of the universe, including the identification of cosmic voids. Without redshift measurements, our maps of the universe would be flat, two-dimensional projections on the sky, showing where galaxies appear without any information about their true depth. It would be like having a map of a city showing where all the buildings are, but not knowing which ones are tall skyscrapers and which are single-story homes, or where the empty lots are hidden behind other buildings. By adding the third dimension of distance derived from redshift, astronomers can transform these flat sky maps into three-dimensional representations of the cosmic web. On these three-dimensional redshift maps, the pattern of filaments, clusters, and voids becomes strikingly clear. Filaments appear as long, string-like collections of galaxies. Clusters are dense knots where these strings intersect. and the cosmic voids, like the Bootes void, stand out as vast, empty regions where there are very few or no galaxies within a specific range of redshifts and sky positions. The Bootes void, for example, was initially discovered by observing a significant gap in the redshift distribution of galaxies in a particular direction. Astronomers looked through a slice of the universe in the constellation Bootes and found that within a certain range of distances, inferred from redshift, there were dramatically fewer galaxies than expected. This gaping hole in the redshift data was the unmistakable signature of the Bootes void, a truly colossal empty region in space. The precision of redshift measurements allows astronomers to define the approximate boundaries of these voids, track their shapes, and estimate their sizes, providing fundamental insights into the universe's large-scale organisation. While redshift is a remarkably powerful tool, it does have some subtleties. Sometimes, galaxies have their own individual motions through space called peculiar velocities, in addition to the overall expansion of the universe. For galaxies relatively close to us, or those within dense clusters, these peculiar velocities can contribute noticeably to their observed redshift or blueshift. However, for the very distant galaxies that define the large-scale structure and the cosmic voids, the cosmological redshift due to the expansion of space is by far the dominant effect. The peculiar velocities become negligible in comparison, allowing astronomers to confidently use redshift as a reliable indicator of cosmic distance and position within the vast cosmic web. In essence, redshift is the cosmic light meter, allowing us to not only gauge how far away galaxies are, but also to chart the magnificent, often empty, architecture of the universe itself. It is through this subtle stretching of light that we have come to understand the true, three-dimensional nature of the cosmos, with its bustling galactic cities and its profound, silent voids. Our understanding of the universe begins, naturally, with our immediate surroundings. We live on a planet called Earth, which orbits a star we call the Sun. Our Sun is just one star among hundreds of billions that make up our home galaxy, the Milky Way. This galaxy is a magnificent spiral, a vast cosmic island of stars, gas and dust, spanning about 100,000 light-years across. It is an immense structure in itself, so large that light takes 100,000 years to travel from one side to the other. For a long time, humanity's perception of the cosmos was largely confined to this galactic home. We saw the band of the Milky Way stretching across our night sky and believed it encompassed the entire universe. However, as scientific instruments improved and our knowledge of cosmic distances expanded, we began to realize that the Milky Way is merely a single star system within a much larger and more intricate cosmic hierarchy. To truly place the Bootes void in its proper context, we must venture far beyond our galactic home, moving through increasingly larger structures until we reach the grand scale of the universe's ultimate architecture. The Bootes void is not just a hole in space, it is a fundamental feature that helps define the boundaries and emptiness within these colossal, cosmic structures, serving as a powerful reminder of the universe's vast, unevenly distributed nature. Our first step beyond our galaxy takes us to our immediate galactic neighbourhood, known as the local group. This is a relatively small collection of galaxies, gravitationally bound together, which includes our Milky Way, its slightly larger spiral cousin the Andromeda Galaxy, and the Triangulum Galaxy, along with about 50 much smaller dwarf galaxies. The local group spans approximately 10 million light-years across. It is like a small town in the cosmic sense, with a few major cities, the Milky Way and Andromeda, and many smaller hamlets, the dwarf galaxies, all tied together by their mutual gravitational attraction. The galaxies within the local group are relatively close to each other, allowing for occasional gravitational interactions and even future mergers, such as the predicted collision between the Milky Way and Andromeda billions of years from now. This local galactic cluster represents the first rung on the ladder of cosmic hierarchy beyond individual galaxies, a gravitationally coherent unit that is distinct from the general field of galaxies. Its existence tells us that even on relatively small scales, galaxies tend to clump together rather than being randomly spread. Moving further out, we encounter the next level of cosmic organization, galaxy clusters. These are far grander than our local group. A galaxy cluster is an enormous collection of hundreds, or even thousands of galaxies, all gravitationally bound together. They are the largest known gravitationally bound structures in the universe, true cosmic cities teeming with galactic life. Galaxy clusters can span several millions to tens of millions of light years across. For example, the Virgo cluster, a relatively nearby galaxy cluster that our local group is slowly being pulled towards, contains over 1,000 galaxies and spans about 10 million light years. Another famous example is the Coma cluster, which is even larger and denser, containing thousands of galaxies. Beyond the visible galaxies, galaxy clusters are also filled with vast amounts of incredibly hot gas that emits X-rays, and, most significantly, colossal amounts of unseen dark matter. In fact, dark matter makes up the bulk of a cluster's mass, providing the immense gravitational pull needed to hold so many galaxies together. Galaxy clusters form in the densest regions of the early universe, where the gravitational pull was strongest, drawing in gas, dust, and galaxies from vast surrounding areas. They are the points of highest density in the cosmic web, serving as powerful gravitational anchors that shape the flow of matter across cosmic distances. The formation of these clusters is a continuous process, with new galaxies falling into them from surrounding filaments, causing them to grow and evolve over billions of years. The next step up in this hierarchy brings us to superclusters. These are even grander structures, representing the largest known aggregations of matter in the universe. Superclusters are not single, gravitationally bound entities in the same way that galaxies or galaxy clusters are. Instead, they are vast, elongated complexes of multiple galaxy clusters, galaxy groups, and individual galaxies, all strung together in long filamentary shapes. They can span hundreds of millions of light years across. Our own local group, along with the Virgo cluster and many other galaxy groups and clusters, is part of an enormous supercluster called Laniakea, which means immense heaven in Hawaiian. The Laniakea supercluster is a truly colossal structure, estimated to be about 500 million light years across, containing the mass of over 100,000 Milky Way-sized galaxies. It is characterized by its flow. All the galaxies within Laniakea are slowly but surely moving inwards, drawn by the combined gravitational pull of its denser regions towards a mysterious gravitational anomaly known as the Great Attractor. Laniakea is just one of many identified superclusters in the universe. Other prominent examples include the Perseus-Pisces supercluster, the Coma supercluster, and the Hercules supercluster, each representing immense cosmic continents of galaxies. Superclusters are essentially the densest, most luminous strands and knots of the vast cosmic web, regions where the universe's matter has congregated on the grandest scales. They are defined not by strong gravitational binding of the whole, but by the overall movement of their component parts towards common centers of gravity. This brings us to the ultimate level of cosmic organization, the cosmic web. The local group, galaxy clusters, and superclusters are all components of this grand universal structure. As discussed in a previous chapter, the cosmic web is a vast interconnected network that permeates the entire observable universe, resembling a colossal three-dimensional sponge or a complex spider web. It is composed of three primary elements: the filaments, which are the long, thread-like strands of galaxies stretching for hundreds of millions of light years; the nodes or clusters, which are the dense intersections where these filaments meet, representing the largest congregations of galaxies; and the voids, which are the vast, underdense spaces that lie between the filaments and clusters. Superclusters, like Laniakea, are essentially the most massive and luminous parts of these filaments and nodes. They represent the densest parts of the cosmic web structure, where gravity has had the most success in pulling matter together over billions of years. Now, where does the Boots void fit into this grand cosmic hierarchy? The Boots void is not a galaxy. It is not part of a galaxy group, nor is it a galaxy cluster or even a supercluster. Instead, it is the exact opposite. The Boots void is one of the largest and most striking examples of a cosmic void, the third fundamental component of the cosmic web. It is a gargantuan hole, a massive bubble of emptiness that exists between these vast filaments and superclusters. It is a region where the cosmic web is essentially missing its threads and knots. Its immense size, estimated at 250 million light-years across, means that it is larger than many individual superclusters, though some of the very largest superclusters can be even more expansive. This surprising fact underscores the profound emptiness of the Bootes void. While a supercluster represents a colossal aggregation of matter, the Bootes void represents a colossal absence of matter. The Bootes void defines the boundaries between these largest aggregations of matter. It sits as a vast, empty buffer zone, separating the dense, bustling regions of the cosmic web. Imagine a series of cosmic continents, the superclusters and filaments, spread across the universe. The Bootes void is like one of the largest oceans separating these continents, a truly immense body of nothingness that emphasizes the clumpy, uneven distribution of matter in the cosmos. It is not an arbitrary empty space, but a gravitationally shaped one, where the surrounding superclusters and filaments have, over cosmic time, pulled matter away from its central regions, leaving behind its characteristic emptiness. Its location within the cosmic web is therefore crucial. It is a defining characteristic of the web's very structure, demonstrating that the universe is not just filled with structures, but also with the vast empty spaces that delineate them. It shows that the universe is not uniformly dense, but rather has extreme variations in matter concentration, from the super-dense cores of galaxy clusters to the profound emptiness of voids like Bootes. Understanding this cosmic hierarchy, from our humble planet to the immense scale of superclusters and the cosmic web, is essential for comprehending the universe's evolution and the role of the fundamental forces that shape it. The existence of the cosmic web, with its intricate pattern of filaments, clusters and voids, is a direct result of the interplay between gravity, which pulls matter together, and the expansion of the universe, which stretches space apart. The Bootes void, as a monumental example of cosmic emptiness, serves as a powerful laboratory for studying these forces. Its large size and extreme underdensity allow astronomers to observe the effects of dark energy, the mysterious force accelerating the universe's expansion in a region where the gravitational pull of ordinary matter is minimized. Thus, by placing the Bootes void in the context of structures far beyond our galaxy, we gain a more complete and awe-inspiring picture of the universe's grand design, a design that is both immensely rich in matter and profoundly empty in vast, silent spaces. The Bootes void, with its colossal dimensions and profound emptiness, is undoubtedly one of the most remarkable structures in the universe, an object that profoundly shaped our understanding of cosmic architecture. However, it is crucial to recognize that the Bootes void is not a singular anomaly. Rather, it is an extreme example of a widespread cosmic phenomenon. The universe is not just filled with galaxies, clusters and superclusters. It is also permeated by vast, underdense regions known as cosmic voids. These empty spaces are fundamental components of the cosmic web, the universe's large-scale structure, just as essential as the galaxy-rich filaments and clusters. While the Bootes void holds a special place due to its scale and its role in early discoveries, many other empty places exist, each contributing to our understanding of the universe's grand, sponge-like design. Studying these other voids helps us to confirm that the Bootes void is part of a broader pattern, allowing us to learn more about the physics that creates and sustains such immense emptiness. Cosmic voids share several general characteristics. They are, by definition, regions of underdensity of galaxies and ordinary matter. This means that the number of galaxies within their boundaries is significantly lower than the average density found throughout the universe. While not absolutely empty of every single atom, their concentration of ordinary matter can be as low as 1/10 of the cosmic average, sometimes even less. Voids typically span tens to hundreds of millions of light-years across, forming vast bubbles in the cosmic web. They are generally considered to be nearly empty of ordinary matter, but they are not entirely devoid of dark matter, and importantly, they are filled with dark energy. Dark matter, though sparse, still provides some gravitational influence, while dark energy is thought to be uniformly distributed everywhere, exerting an expansive push that contributes to the growth and increasing emptiness of these voids. This accelerated expansion is a key feature of all voids, making them valuable laboratories for studying dark energy as its effects are less masked by gravity in these underdense environments. All voids also contain a scattering of lonely galaxies, which are isolated from their peers and often exhibit unique evolutionary characteristics due to their isolated environments. While they share these fundamental traits, cosmic voids are far from uniform. There is a great diversity of voids in terms of their size, shape, and internal structure. Not all voids are as gargantuan as the Bootes void, which, with its approximate 250 million light-year diameter, is among the very largest known. Many voids are smaller, perhaps only 50 or 100 million light-years across. The sizes of voids often correlate with the density of the surrounding cosmic web. Larger voids tend to be found between larger, more massive superclusters. Their shapes are also highly irregular, rarely perfect spheres. Instead, they often appear elongated, twisted, or somewhat amorphous, reflecting the complex, non-uniform gravitational flows that have pulled matter away from their centers over billions of years. Some voids might be relatively isolated, like the Bootes void, while others might be interconnected, forming vast void complexes that stretch across enormous cosmic distances, like vast empty channels within the cosmic web. This variation in size and shape provides important clues about the initial conditions of the universe and the exact interplay of gravity and dark energy in shaping the cosmos. One notable example of another empty place is the local void. This void is much closer to us than the Bootes void, and it directly influences our own local cosmic neighborhood. The local void is a vast, relatively empty region of space that separates our local group of galaxies, which includes the Milky Way and Andromeda, from other nearby galaxy clusters and superclusters. It lies on one side of our local group, effectively pushing us away through its gravitational emptiness, while the gravitational pull of nearby denser regions like the Virgo cluster pulls us towards them. The local void is believed to be influencing the peculiar velocity of our local group, contributing to our motion through space. While smaller than the Bootes void, spanning perhaps 100 to 150 million light-years, the local void is significant because of its proximity and its direct impact on our understanding of our own motion within the cosmic web. Its study helps to confirm that voids are not just theoretical constructs, but exert real gravitational influence on surrounding matter. Another large structure is the northern local supervoid, also sometimes referred to as the sculptor void. This is a vast, roughly spherical region of space, about 300 million light-years in diameter, that is significantly underdense in galaxies. It is located relatively close to our local group, surrounding parts of the local supercluster and extending outwards. While less famous than the Bootes void, it is another compelling example of a truly large empty space, contributing to the overall foam-like structure of the universe. Its study helps astronomers to understand the distribution of voids and their impact on the flows of galaxies in the local universe. Perhaps one of the most intriguing and actively researched empty places is the potential Eridanus supervoid, which has been linked to the CMB cold spot. The cosmic microwave background, or CMB, is the faint afterglow radiation from the Big Bang, covering the entire sky. While incredibly uniform, the CMB map shows tiny variations in temperature. One particular region, known as the CMB cold spot, is unusually cold, a very large patch of sky that is significantly colder than its surroundings. One leading explanation for this cold spot is that the CMB photons passing through it have traversed a massive, exceptionally empty cosmic void. This hypothetical Eridanus supervoid would need to be truly immense, perhaps 1 billion light-years across, making it potentially even larger than the Bootes void. If confirmed, its existence would provide strong evidence for how large voids can grow and how they can leave an imprint on the very oldest light in the universe. The Eridanus supervoid is a subject of ongoing research, involving complex analyses of galaxy surveys to try and confirm its existence and map its true extent in 3 dimensions. Its potential size and its connection to the CMB cold spot make it a fascinating example of a void that could be even more extreme than Bootes. All these voids, from the local void to the Bootes void and the potential Eridanus supervoid, share fundamental similarities in their formation and characteristics. They are all regions of space where the initial tiny density fluctuations in the early universe were slightly lower than average. Over cosmic time, gravity pulled matter away from these underdense regions towards the denser filaments and clusters of the cosmic web. All voids are continuously expanding due to the general expansion of the universe, and their emptiness is further exaggerated by the pervasive push of dark energy, which becomes dominant where matter's gravity is weak. They all contain a very sparse population of lonely galaxies that offer unique insights into galaxy evolution in isolation. In essence, they are all manifestations of the same underlying physical processes that have shaped the universe into its intricate web-like structure, where matter clumps in some places and is conspicuously absent in others. They are all windows into the physics of gravity, dark matter, and dark energy at play on the larger scales. However, there are also notable differences among these voids. The most obvious difference is size. While the Bootes void is exceptionally large, many other voids are smaller. The sheer scale of the Bootes void sets it apart and made its discovery particularly shocking. Another difference can be their degree of emptiness. While all are underdense, some might be slightly more or less sparse than Bootes, depending on their formation history and local gravitational environment. The isolation of the Bootes void's lonely galaxies is also particularly extreme due to its immense size, making them arguably the most isolated galaxies known. The Bootes void also holds a unique place in scientific history as one of the very first and most dramatic large voids to be identified, providing initial, compelling evidence for the cosmic web concept and paving the way for the systematic search and study of other voids. Its discovery was a turning point, showing the scientific community that such colossal emptiness was not only possible, but a fundamental feature of the universe. The importance of studying multiple voids across the universe cannot be overstated. By comparing and contrasting different voids, astronomers can gain a more comprehensive understanding of their statistical properties, how common they are, their typical sizes, their distribution, and their average emptiness. This helps to test and refine cosmological models of structure formation, ensuring that our theories accurately predict the full range of cosmic structures, from the smallest galaxies to the largest voids. Voids, particularly those with extreme properties like the Bootes void or the CMB cold spot, serve as crucial probes for understanding dark energy. By observing how these vast empty regions expand and how their few inhabitants evolve, scientists can gather data that helps to constrain the properties of dark energy and shed light on its mysterious nature. They are also vital for understanding how galaxy evolution is affected by environment, providing a counterpoint to studies of galaxies in dense clusters. Furthermore, astronomers are increasingly looking at void networks, how individual voids might connect to form larger interconnected complexes, creating vast empty channels within the cosmic web. This concept suggests that voids are not just isolated bubbles, but part of an intricate multi-scale system of emptiness. The universe's large-scale structure is a dynamic interplay of concentrations and rarefactions, and voids are not passive spaces but active regions where the cosmic expansion is most clearly expressed. The Bootes void, while a distinct entity, is ultimately part of this larger interconnected system of cosmic emptiness, reminding us that the universe is a place of profound structure, where even nothingness plays a crucial role in the grand cosmic design. Imagine, if you can, a civilization not unlike our own, with intelligent beings, advanced technology, and a deep yearning to understand their place in the cosmos. Now, imagine this civilization exists not in a bustling galactic neighborhood, nor in a vibrant cluster of stars, but on a planet orbiting a star that is itself part of a small, isolated galaxy, located deep within the Bootes void. This speculative journey takes us to the heart of cosmic emptiness, exploring what life, science, and philosophy might be like for a species born and raised in such an extraordinarily isolated corner of the universe. Their experience of the cosmos would be profoundly different from ours, shaped by the vast, silent chasm that surrounds them, a cosmic reality defined by scarcity and an almost unimaginable sense of separation. The most striking and immediate difference for such a civilization would be their view of the night sky. For us on Earth, even in areas with significant light pollution, the brightest stars of our own Milky Way galaxy are visible, painting a broad, luminous band across the heavens. From dark sky sites, faint smudges of other nearby galaxies like Andromeda can sometimes be seen with the naked eye, hinting at a universe beyond our own star system. Our sky is alive with the light of billions of stars and millions of galaxies, each a distant beacon of activity. But for a civilization in the Boots Void, the night sky would be dominated by an overwhelming, profound darkness. Their own galaxy, perhaps a faint spiral or an irregular collection of stars, would be the sole luminous structure visible to their unaided eyes, while the stars within their own galaxy would still glitter with familiar brilliance, forming their own unique patterns and constellations. The vast, empty space beyond would appear as a boundless, inky blackness, largely devoid of any distant discernible light. The nearest other galaxy to them would be tens of millions, or even hundreds of millions of light-years away. This means that any light from these incredibly distant neighbours would be so faint by the time it reached their planet that it would be entirely invisible without extremely powerful telescopes. Unlike Earth, where galactic collisions and near misses are rare but visible phenomena such as the impending collision between the Milky Way and Andromeda, for these void dwellers such events would be utterly beyond their observational reach, occurring in a cosmic distance so vast as to be functionally irrelevant to their daily lives or even their astronomical studies for a very long time. The vibrant, bustling cosmic web with its intricate filaments and dense galaxy clusters would be an entirely alien concept to their early astronomers. Their view would be of their own galaxy as an island, possibly the only island, in an endless empty sea. This visual starkness would deeply influence their early understanding of the universe, perhaps leading to a belief in a much smaller, more isolated cosmos, with their galaxy at its unique, solitary centre. The challenges for their early astronomers in understanding the true nature of the universe would be immense. For us, the discovery of other galaxies, then galaxy clusters, and eventually the cosmic web, was a gradual process of pushing the limits of our telescopes and refining our methods for measuring cosmic distances. We could observe the clustering of galaxies relatively easily. For a void civilization, simply detecting the existence of other galaxies would be a monumental achievement, requiring technology far beyond what Earth astronomers possessed in the early days of galactic discovery. Even once detected, measuring their distances accurately would be incredibly difficult due to their extreme faintness and isolation. The concept of redshift, crucial for mapping cosmic distances, would still apply, but the light signals would be so weak that gathering enough photons to analyze a galaxy's spectrum would demand immense light-gathering power and incredibly long observation times. Their equivalents of Edwin Hubble would face a far steeper climb to establish the expansion of the universe, as their immediate surroundings would be gravitationally calm, and the recession velocities of the few distant galaxies would be challenging to measure precisely. Their cosmology, the study of the universe as a whole, would likely develop along different lines. Without readily observable galaxy clusters or filaments, the idea of a cosmic web might remain elusive for millennia. They might first postulate a universe of scattered, isolated galaxies, rather than one of interconnected structures. The concept of dark matter, inferred from the rotation of their own galaxy, would still be discoverable. However, the influence of dark energy, which causes space to accelerate its expansion, might actually be more apparent to them at an earlier stage of their cosmological studies. Because their galaxy is in such a gravitationally weak environment, the expansive push of dark energy would be less masked by the local gravitational pull of surrounding matter. They might detect the accelerating expansion of the universe more clearly and more quickly than we did, simply because their cosmic neighbourhood offers a cleaner observational laboratory for this mysterious force, free from the strong gravitational perturbations of dense clusters. This early realization about dark energy could profoundly shape their physics and their understanding of the universe's ultimate fate, perhaps leading to a more immediate sense of impending cosmic loneliness. The technological trajectory of a void civilization might also differ, with no nearby galaxies presenting a potential target for interstellar probes, and certainly no easy opportunity for intergalactic travel. Their focus might shift. Early space exploration would likely be confined to their own star system, then within their own galaxy. The concept of exploring other galaxies might seem utterly unfeasible, an abstract theoretical possibility rather than a practical goal for countless generations. The immense distances would make sending even unmanned probes an undertaking of unimaginable timescales, perhaps requiring entirely new propulsion technologies that we can only dream of. This lack of external galactic targets might either stifle their ambition for vast cosmic exploration, or, conversely, ignite an even greater drive to develop revolutionary technologies capable of bridging these immense, empty gulfs. The motivation might be philosophical, a desperate search for other life, or a fundamental curiosity to confirm whether their galaxy truly is alone. From a societal and philosophical perspective, life in the void would carry a profound sense of isolation. The question, "Are we alone?" would take on an entirely different weight. For us, finding extraterrestrial life might simply be a matter of time and technological advancement, given the billions of stars in our galaxy and the millions of galaxies in our visible universe. For them, the silence of the void would amplify the feeling of being truly unique, perhaps even the sole spark of intelligence in an otherwise empty cosmos. This could lead to a deep philosophical introspection, perhaps fostering a culture that cherishes their own existence as an extraordinarily rare cosmic anomaly. Religion and spiritual beliefs might center around themes of isolation, resilience, and the preciousness of their singular existence. The absence of external galactic threats, no fear of merging with another galaxy, no worries about cosmic rays from distant supernovae bombarding their system with significant frequency, would mean that their understanding of cosmic dangers would be largely confined to phenomena within their own galaxy or star system. This might lead to a more inward-looking civilization, focused on the longevity and sustainability of their own galactic home, rather than contemplating threats from beyond. Their perception of cosmic time would also be unique. When they finally did develop telescopes powerful enough to detect the incredibly faint light from the nearest other void galaxies, or even the luminous walls of the cosmic web at the void's distant edges, that light would be ancient. It would have travelled for hundreds of millions, or even a billion years to reach them. This means they would always be looking far back into the past. Their view of the present universe beyond their immediate galactic vicinity would be permanently out of reach. This could instill a deep appreciation for cosmic history, but also a poignant awareness of the unbridgeable gulf between them and the current state of the wider cosmos. Their understanding of now would be strictly local, confined to their own galaxy, while the rest of the universe would always be seen through the veil of immense time delays. The concept of real-time interactions with any hypothetical distant civilizations would be entirely theoretical, relegated to the realm of philosophical debate rather than practical communication. Resource management for a void civilization would be self-contained within their single galaxy. There would be no possibility of importing rare elements or technologies from other galaxies, or escaping to a new galactic home should theirs face a catastrophic event. Their survival would depend entirely on the resources within their own galactic island. This might foster a strong sense of environmental stewardship and long-term planning, as they would be acutely aware of the finite nature of their immediate cosmic endowment. Population growth and technological expansion would be bounded by the limits of their own galactic system, potentially leading to different societal structures and priorities compared to a civilization that views the entire universe as a potential playground or resource pool. The challenges of sustaining a civilization for billions of years within a single, isolated galaxy might push them towards extreme efficiency, recycling, and innovation in ways we're only beginning to consider. In terms of biological evolution, while highly speculative, the void environment might have subtle influences. Cosmic rays, high-energy particles from supernovae and other extreme cosmic events are a factor in radiation exposure for life. If a void galaxy is truly isolated, the flux of cosmic rays from external galactic sources might be significantly lower compared to galaxies in denser, more active regions of the cosmic web. This could, theoretically, lead to slightly different evolutionary pressures related to radiation tolerance, perhaps allowing for different forms of life to flourish, or simply resulting in a slightly lower mutation rate from external cosmic sources. However, internal galactic sources of cosmic rays would still exist, so this effect would be marginal at best. The primary biological challenges would still be planetary and intragalactic, rather than intergalactic. Ultimately, a civilization in the Booty's void would experience the universe in a way that is almost diametrically opposed to our own. While we are part of a bustling galactic filament, with millions of galaxies visible in our observable universe, they would exist in a realm of profound cosmic emptiness. Their quest for knowledge, for meaning, and for connection would be profoundly shaped by the vast silent gulfs that surround them. Their journey of cosmic discovery would be one of incredible patience, ingenuity, and a deep appreciation for the rare, isolated sparks of light that define their existence. The Booty's void, therefore, is not just a scientific curiosity. It is a thought experiment that stretches our imagination, forcing us to consider the myriad ways life might perceive and interact with a universe that is far more diverse in its structures and its emptiness than we often assume. Their existence would be a poignant reminder that while the universe is vast, it is also incredibly uneven, creating islands of life and thought separated by unimaginable gulfs of profound, eternal silence. The universe is a treasure trove of wonders, but many of its most profound secrets are hidden not in bright glowing objects, but in the vast, seemingly empty spaces that define its grand architecture. Cosmic voids like the immense Booty's void are regions of profound underdensity, where visible matter such as stars and galaxies is incredibly scarce. Trying to study these empty places presents a unique and formidable set of challenges for astronomers. It is not like observing a bright star or a nearby galaxy, which emits abundant light. Instead, it is akin to trying to map an invisible ghost, gathering clues from the subtle ways it influences its surroundings, or from the rare, faint whispers of light from the few, isolated objects that happen to reside within its boundaries. Overcoming these challenges requires immense ingenuity, cutting-edge technology, and painstaking effort, pushing the very limits of what our instruments can detect and what our minds can comprehend. The primary challenge in observing voids is their very definition. They contain very little visible matter. This means there are few, if any, direct light sources within them that our telescopes can easily pick up. When astronomers study galaxies, they rely on the light emitted by billions of stars and glowing gas. When they study galaxy clusters, they can also detect the hot X-ray emitting gas that permeates the space between galaxies. But in a void, these sources are either almost entirely absent or so incredibly sparse that their light is stretched thin across unimaginably vast distances. This makes the targets incredibly faint and difficult to distinguish from the background noise of cosmic radiation or instrumental interference. For the few galaxies that do reside within a void, their light has travelled for hundreds of millions of years, fading and stretching along the way, further complicating detection. It is like trying to photograph a single dim candle flame from across an entire continent. The signal is almost entirely lost in the immense distance and ambient light. To address the challenge of faintness, astronomers rely on immense light-gathering power. This means using the largest telescopes available. Ground-based optical telescopes with mirrors many meters in diameter are designed to act as giant light buckets, collecting as many photons as possible over extended periods. Instruments like the European Southern Observatory's Very Large Telescope, VLT, in Chile, with its 4 individual 8.2-meter telescopes that can work together, or the twin 10-meter Keck telescopes in Hawaii, are crucial. These behemoths can stare at a single patch of sky for hours, even nights, accumulating enough faint light to build a detectable signal from distant sparse galaxies. The longer the exposure time, the more photons are collected, and the clearer the image or spectrum becomes. However, even with these giants, the sheer volume of a void means that finding and meticulously observing its sparse inhabitants is a time-consuming and resource-intensive endeavour. Space telescopes like the Hubble Space Telescope and the newer James Webb Space Telescope, JWST, are also indispensable for observing the unseen. Being above Earth's atmosphere, they are not hampered by atmospheric blurring or absorption of light. This allows them to capture sharper images and detect fainter objects than ground-based telescopes, particularly at wavelengths that are absorbed by the atmosphere. JWST in particular is revolutionary for void studies. It is exquisitely sensitive to infrared light. As light from distant galaxies travels through the expanding universe, it gets stretched or red-shifted towards longer, redder wavelengths, often moving out of the visible light spectrum and into the infrared. JWST's infrared capabilities mean it can detect this highly redshifted light from the very faint, distant galaxies that populate the edges of voids or even reside within them, providing a clearer view of these elusive objects than ever before. This ability to capture deeply redshifted light is fundamental to mapping the void's true extent and content. The most critical observational method for mapping voids is the Galaxy Redshift Survey, as explained in a previous chapter. This is the primary tool for creating three-dimensional maps of the universe. To map a void, astronomers need to know not just where galaxies appear on the sky, but also their precise distances. This is achieved by measuring the redshift of their light using spectrographs. A spectrograph precisely splits a galaxy's light into a spectrum, allowing astronomers to identify the unique fingerprints of elements, spectral lines, and measure how much they have shifted towards the red end of the spectrum. This shift directly corresponds to how fast the galaxy is receding due to the expansion of space, and by extension, how far away it is. For studying voids, this is paramount because it allows astronomers to identify the gap in galaxy distribution at specific distances. If a large volume of space, at a certain redshift, distance, shows a significant drop in the number of galaxies compared to what is expected, that is the unmistakable signature of a cosmic void. Large-scale redshift surveys, such as the Sloan Digital Sky Survey, SDSS, and the upcoming Dark Energy Spectroscopic Instrument, DESI survey, are massive undertakings specifically designed to map millions of galaxies across vast swathes of the sky. These surveys use automated systems to observe thousands of galaxies simultaneously, greatly increasing efficiency. The data from these surveys are then compiled into colossal three-dimensional catalogues of galaxy positions. It is within these cosmic maps that voids like booties are revealed. Specialized data analysis techniques are then applied to these maps. Astronomers use algorithms that identify regions where the galaxy density falls below a certain threshold, effectively outlining the boundaries of the voids. These algorithms can identify voids of various sizes and shapes, and quantify their emptiness by calculating the density contrast, how much sparser the void is compared to the average cosmic density. The challenge here is statistical. It's not just about finding an empty space, but demonstrating that its emptiness is statistically significant, and not just a random fluctuation in galaxy distribution. Sophisticated software is needed to process and visualize these immense datasets, turning raw light measurements into a coherent picture of the universe's web-like structure. One particularly difficult aspect is confirming the presence of galaxies within voids and studying their properties. The few, lonely galaxies residing deep within the Boots void are not easy to find or study. Astronomers must carefully confirm that these galaxies are indeed physically located within the void's boundaries at the correct redshift, distance, and are not simply foreground or background galaxies that happen to be in the same direction on the sky. This requires meticulous follow-up observations and precise distance measurements. Once confirmed, studying these void galaxies is challenging because of their inherent faintness and isolation. Their light is extremely weak, and their features are often subtle. Despite this, studying these galaxies is crucial. Their unique evolutionary pathways, unaffected by the gravitational interactions common in denser environments, provide a crucial control group for understanding how galaxies form and evolve. They allow astronomers to isolate the effects of a galaxy's internal processes from the influence of its environment, which is a major area of research in modern astrophysics. Beyond directly mapping galaxies, astronomers also employ indirect methods to observe and characterize voids. One fascinating technique involves studying the cosmic microwave background, CMB, the faint afterglow of the Big Bang. As CMB photons, the oldest light in the universe, travel across billions of light years to reach us, they pass through various cosmic structures. Their energies are slightly affected by the gravitational potentials of these structures. When CMB photons pass through a large cosmic void, they can experience a tiny drop in temperature compared to photons passing through denser regions. This subtle effect, known as the integrated Sachs-Wolf, this W effect, leaves a faint cold spot on the CMB map. While incredibly difficult to detect due to its faintness, a few large cold spots on the CMB map have been observed, and some, like the famous CMB cold spot, are hypothesized to be caused by the presence of super-large voids, such as the potential Eridanus supervoid. Detecting such correlations between CMB cold spots and galaxy underdensities would provide independent and powerful evidence for the existence and properties of these voids, particularly their gravitational influence over cosmic scales. Another indirect method, though still very challenging for voids, is weak gravitational lensing. This technique measures the subtle distortions of the light from very distant background galaxies as it passes through the gravitational fields of intervening matter, including dark matter. Even the sparse dark matter within a void can, in principle, cause tiny, systematic distortions of background light. By mapping these subtle distortions over large areas, astronomers could potentially infer the distribution of dark matter within voids, even though it is invisible. This is an extremely difficult measurement because the lensing signal from a void is very weak, but it holds promise for future observations with even more sensitive instruments. Finally, looking to the future, radio astronomy offers exciting new possibilities for observing the unseen matter within voids. While voids are sparse in galaxies, they are still theorized to contain a very tenuous diffuse gas, primarily neutral hydrogen, left over from the early universe. This neutral hydrogen emits radio waves at a very specific wavelength of 21 centimeters. Large radio telescopes and arrays, like the Square Kilometre Array, SKA, currently under construction, are being designed with the sensitivity to detect this faint 21 centimeter emission from the incredibly sparse hydrogen gas within voids. If successful, this would provide a direct way to map the distribution of ordinary matter within voids, offering an unprecedented look into their true emptiness and how they are evolving. This would be a crucial step beyond just mapping the absence of galaxies, to mapping the very presence of diffuse gas, confirming the models of void formation in exquisite detail. Gravity, often described as the weakest of the four fundamental forces of nature, might seem an unlikely candidate to be the primary architect of the universe's largest and most magnificent structures. Yet, over the immense timescales of cosmic history, spanning billions of years, gravity's relentless and pervasive pull has sculpted the cosmos into the intricate web-like tapestry we observe today. It is the force responsible for gathering diffuse gas into shining stars, stars into galaxies, and galaxies into colossal clusters and filaments. But, perhaps counterintuitively, gravity is also equally responsible for creating the vast empty regions of space known as cosmic voids, like the immense Bootes void. These seemingly contradictory roles reveal gravity's profound influence on the distribution of matter in the universe, demonstrating how its attractive power not only builds up the dense cosmic cities, but also clears out the immense cosmic deserts that lie between them. It is a ceaseless, universal sculptor, working patiently to organize the scattered ingredients of the cosmos. At its most fundamental level, gravity is simply the attraction between any two objects that have mass or energy. The more massive an object, the stronger its gravitational pull. The closer two objects are, the stronger the pull between them. This simple rule, discovered by Isaac Newton and later refined by Albert Einstein in his theory of general relativity, is the driving force behind everything from an apple falling to Earth to the complex dance of galaxies across billions of light years. In the early universe, after the Big Bang, the cosmos was a hot, dense, nearly uniform soup of matter and energy. But crucially, it was not perfectly uniform. There were tiny, almost imperceptible variations in density, microscopic ripples where matter was ever so slightly more concentrated in some places and slightly less concentrated in others. These primordial fluctuations, as they are called, were the initial seeds from which all subsequent structure would grow, and gravity was the gardener. Imagine, if you will, this early universe as a vast, calm ocean with extremely subtle swells and depressions. In the regions where there was a tiny bit more matter, gravity would naturally be a tiny bit stronger. This slightly stronger gravitational pull would begin to draw in even more surrounding matter. It is a cumulative effect. a kind of cosmic snowball rolling downhill. As more matter was attracted to these slightly denser regions, their mass would increase, and consequently, their gravitational pull would become even stronger. This stronger pull would then draw in even more matter, accelerating the process. This positive feedback loop is known as gravitational instability. It explains how initially tiny overdensities in the early universe grew steadily larger over vast periods of time, gradually accumulating more and more material. These growing clumps of matter were the embryonic forms of what would eventually become the galaxies, galaxy clusters, and the great filaments of the cosmic web. Conversely, in the regions where there was initially a tiny bit less matter than the average, gravity's pull was correspondingly weaker. As the more massive surrounding regions began to pull in matter, they drew material away from these underdense areas. These underdense regions, lacking a strong central gravitational attraction, were unable to hold on to their sparse material as effectively. Instead, their matter was slowly but surely siphoned away, flowing towards the more gravitationally attractive, denser regions. This continuous outflow of matter from the underdense regions further depleted them, making them even emptier. Thus, as gravity worked to pull matter together in some places, it simultaneously worked to pull matter away from other places, leaving them increasingly vacant. The universe, through gravity, was effectively sorting itself out, creating regions of profound density and regions of profound emptiness. The Booty's void is a prime example of one of these underdense regions that has been gravitationally emptied out over cosmic time. The role of dark matter in this process cannot be overstated. Dark matter is a mysterious substance that we cannot see directly because it does not interact with light or any other form of electromagnetic radiation. However, it makes up about 85% of all matter in the universe, far outweighing the ordinary matter that forms stars and galaxies. Because it is so much more abundant, dark matter's gravitational influence is absolutely dominant in the formation of large-scale structures. The tiny density fluctuations in the early universe were primarily fluctuations in dark matter density. These initial, invisible clumps of dark matter provided the deep gravitational wells that acted as the primary gathering points for both ordinary matter and more dark matter. Ordinary gas and dust, feeling the pull of these invisible dark matter concentrations, would fall into them, cool, and eventually condense to form stars and galaxies. Without the vast gravitational scaffolding provided by dark matter, the ordinary matter alone would have been too diffuse, and its gravity too weak to overcome the rapid expansion of the early universe and form the distinct galaxies and clusters we observe today. The universe would likely be a much more uniform, less structured, and far less interesting place. Therefore, the cosmic web, with its intricate pattern of filaments, clusters, and voids, is fundamentally a dark matter structure. The filaments are giant, elongated strands of dark matter, pulling in galaxies along their length. The clusters are massive, dense knots of dark matter, acting as the gravitational hubs of the universe, and the voids, like booties, are the vast empty bubbles where dark matter itself is significantly underdense. It is the gravitational behavior of this pervasive, invisible dark matter that largely dictates where the ordinary, luminous matter ultimately congregates and where it is absent. The visible galaxies we see are simply tracing the underlying gravitational landscape sculpted by dark matter. The emptiness of the Booty's void is thus largely a reflection of a region that was initially very low in dark matter, which consequently exerted less gravitational pull, causing it to lose material to its denser, dark matter-rich neighbours. Consider the process across different scales. On the smallest scales, within collapsing gas clouds, gravity pulls individual atoms and molecules together, leading to the formation of stars. These stars, once formed, exert their own gravitational pull, gathering into star clusters. On slightly larger scales, billions of stars, along with vast amounts of gas and dust, are gravitationally bound together to form galaxies, like our own Milky Way. The spiral arms and the overall shape of a galaxy are shaped by the gravitational interactions between its myriad components, all held within a much larger dark matter halo. Moving to even larger scales, gravity continues its work. Individual galaxies, like the Milky Way and Andromeda, exert gravitational pull on each other, forming galaxy groups, like our local group. These groups, in turn, are drawn towards even larger concentrations of matter, forming galaxy clusters, which can contain hundreds or thousands of galaxies. The immense gravity of these clusters pulls in galaxies from surrounding regions, causing them to move towards the cluster's core. These clusters are often connected by long, thin strands of galaxies, the filaments of the cosmic web. These filaments are also gravitationally driven, acting as cosmic highways along which galaxies flow towards the most massive clusters. The entire network of filaments and clusters represents the regions where gravity has successfully overcome the universe's expansion, gathering matter into enormous, dense structures. And then we have the voids. These are the complementary features to the filaments and clusters. As gravity pulls matter into the web-like structures, it simultaneously creates the empty spaces. The Bootes void is an enormous example of such a gravitationally driven emptying process. Its vastness means that it was initially a particularly large and pronounced underdensity in the early universe, a region with less dark matter than most. Over billions of years, the collective gravitational pull of the surrounding denser filaments and clusters acted like a cosmic siphon, drawing matter away from the Bootes void, leaving it increasingly desolate. The few, lonely galaxies that remain within the void are those that either formed from residual slightly denser pockets within the void itself, or were simply too isolated and small to be significantly pulled out by the surrounding structures. Their very isolation is a testament to the immense gravitational power that has cleared out their surroundings. The timescale over which gravity acts is crucial. It is not an instantaneous process. The universe has been evolving for roughly 13.8 billion years since the Big Bang. Over these immense timescales, even the incredibly weak gravitational pull between widely dispersed particles can have a cumulative effect. The subtle variations in density that existed in the very early universe, when magnified by the continuous action of gravity over billions of years, led to the grand structures we see today. Gravity's patient, persistent pull is what allows small overdensities to grow into structures massive enough to overcome the overall expansion of the universe and hold themselves together, while simultaneously ensuring that the underdense regions become ever more sparse. The universe is not a static, unchanging arena where cosmic events unfold. Instead, it is a dynamic, living entity, continuously growing and evolving. One of the most revolutionary discoveries of the 20th century was that the universe is not only expanding, but its expansion is actually accelerating. This ongoing expansion of space itself has profound implications for every structure within the cosmos, from individual galaxies to the colossal cosmic web, and it plays a particularly critical role in the growth and development of cosmic voids, like the immense Bootes void. While gravity works to pull matter together, the universe's expansion works to pull space apart, and in the emptiest regions of the cosmos, this expansive push becomes the dominant force, actively making these already sparse areas even emptier. The concept of the expanding universe was first firmly established by the American astronomer Edwin Hubble in the late 1920s. By observing distant galaxies and measuring their redshift, the stretching of light waves as objects move away from us, Hubble discovered that almost all galaxies outside our immediate galactic neighbourhood are moving away from us, and the farther away a galaxy is, the faster it is receding. This relationship, known as Hubble's law, was a groundbreaking realization. It wasn't that galaxies were simply flying away from a central point in space like shrapnel from an explosion. Instead, it was space itself that was expanding, carrying the galaxies along with it, much like dots drawn on the surface of an inflating balloon. The dots themselves don't move on the surface, but the stretching of the surface increases the distance between them. This cosmological expansion affects everything in the universe on large scales. To fully grasp how expansion influences voids, it is important to distinguish between motion through space and the expansion of space. On relatively small scales, within gravitationally bound structures like our solar system, individual galaxies, and even galaxy clusters, gravity is strong enough to overcome the force of cosmic expansion. Our Earth is not expanding away from the Sun, nor is the Sun expanding away from the centre of the Milky Way, and the Milky Way is not expanding away from the Andromeda Galaxy within our local group. In these cases, gravity's attractive pull is far stronger than the expansive stretch of space over those relatively short distances. These structures are gravitationally bound and remain intact, acting as islands that are being carried along by the expanding cosmic ocean, but not expanding internally. However, on very large scales, beyond galaxy clusters and superclusters, the gravitational pull between widely separated galaxies becomes weak enough that it can no longer fully counteract the overall expansion of space. This is where the universe's expansion truly dominates. It is at these grand intergalactic scales that the stretching of space becomes evident and begins to profoundly influence the distribution of matter. The cosmic web, with its filaments and clusters, represents the regions where gravity has successfully clumped matter together. The voids, on the other hand, are the regions where gravity has been weakest, and where the expansion of space has therefore had the most pronounced effect. The universe's expansion actively contributes to the growth and development of cosmic voids. Imagine a vast interconnected network of rubber bands, with marbles stuck at the intersections and along the strands. As you pull the entire network outward, representing the expansion of space, the marbles at the intersections, galaxy clusters, might remain relatively close to each other due to strong glue, gravity. But the sections of the rubber bands between the marbles, especially in areas where there were already fewer marbles, the voids, will stretch out significantly. This stretching makes the already sparse spaces even larger and emptier. As space expands, the distance between any 2 points within a void increases. If there were already few particles or galaxies in that space, the expansion simply pulls them further apart, making the density even lower. This is a continuous process. As the universe ages, voids do not remain static holes. They actively grow, becoming increasingly vast and desolate. The Bootes void, already immense at its discovery, continues to expand and grow emptier with every passing moment of cosmic time. A particularly crucial factor in the current era of the universe's expansion is dark energy. For much of the universe's history, gravity was dominant, slowly decelerating the expansion. However, in the late 1990s, observations of distant supernovae revealed a stunning truth. The universe's expansion is not slowing down, but actually speeding up or accelerating. This accelerated expansion is attributed to dark energy, a mysterious force or property of space itself that exerts a repulsive, anti-gravitational push. Dark energy is believed to be uniformly distributed throughout all of space, meaning it has the same density everywhere, whether in a dense galaxy cluster or a vast cosmic void. The presence of dark energy significantly enhances the growth of voids. In dense regions of the cosmic web, the strong gravitational pull of concentrated matter largely counteracts the repulsive push of dark energy. While dark energy is present there, its effects are masked by the overwhelming gravitational attraction. But in the vast, underdense regions of cosmic voids, where the amount of ordinary and dark matter is exceptionally low, gravity's pull is greatly diminished. In these environments, the expansive, repulsive push of dark energy becomes dominant. There is simply not enough local gravity to hold back the accelerating expansion. As a result, voids are not just expanding passively, they are being actively pushed apart by dark energy at an accelerating rate, causing them to grow even faster and become even emptier than they would under gravity alone. They are the parts of the universe where the stretching power of dark energy is most clearly expressed, unhindered by strong gravitational binding. This makes cosmic voids, especially very large ones like the Bootes void, invaluable laboratories for studying dark energy. By meticulously observing how voids evolve over time, how quickly they expand, and how the few galaxies within them are distributed and moving, astronomers can gather crucial data to test different models of dark energy. If dark energy is indeed a constant property of space, then voids should expand in a very specific, predictable way. If its properties change over time, or if its density varies, then the behavior of voids would reflect these differences. The unique environment of voids, where gravity from matter is minimal, allows cosmologists to isolate and measure the effects of dark energy more directly than in other parts of the universe. The Bootes void, being such a large and well-defined example of cosmic emptiness, provides a prime observational target for these critical studies, offering insights into one of the biggest mysteries in modern physics. The continuous expansion of the universe, accelerated by dark energy, paints a fascinating picture for the very distant future of cosmic voids. As the universe continues to expand at an accelerating rate, the distances between galaxies that are not gravitationally bound will grow exponentially. Eventually, galaxies beyond our own local group will recede so fast that their light will be stretched so much, highly redshifted, that it will become undetectable, effectively moving them beyond our observable horizon. The filaments of the cosmic web will become increasingly stretched and thin, and the connections between galaxy clusters will weaken and eventually break. Voids, already immensely empty, will grow even larger and more profoundly desolate. Any lonely galaxies within these voids would become even more isolated, eventually losing sight of any other galaxies in the universe as they recede beyond what can be observed. The ultimate fate, perhaps trillions of years from now, could be a universe where each gravitationally bound galaxy or small cluster exists as an isolated island in an ever-expanding, silent and empty cosmic ocean, with the voids representing the ultimate expression of this accelerating cosmic solitude.